Space has always been a realm of intrigue and uncertainty, a vast, enigmatic expanse that continues to challenge our understanding despite the immense strides made by science. Each new discovery leads to more questions, more curiosities, and more mysteries about the universe that seem to evade even the most advanced minds. From bizarre signals traversing across the cosmos to planets that defy all known physical laws, the cosmos is filled with phenomena that resist classification. What then lurks in the uncharted and shadowed corners of space? Could there be forces beyond our comprehension, forces shaping reality itself, waiting to be discovered? One particular celestial mystery, Tabby's star, has captivated the scientific community for years, sparking debates, investigations, and theories that range from the plausible to the extraordinary. Officially known as KIC 8462852, this distant star resides roughly 1,400 light-years from Earth, nestled in the constellation Cygnus. Its unusual behavior has left astronomers scrambling to find answers. Unlike most stars that follow predictable cycles of dimming and brightening, Tabby's star exhibits sudden, erratic dips in brightness, sometimes up to 20% without any clear cause. What makes this even more perplexing is that, despite years of observation, no definitive explanation has emerged to account for its erratic behavior. The strange fluctuations were first noticed by citizen scientists working on the Planet Hunters project, a crowdsourced effort designed to spot exoplanets by analyzing changes in the brightness of distant stars. The data they uncovered from NASA's Kepler Space Telescope revealed that Tabby's star's brightness fluctuated in ways no one had seen before. These dips weren't subtle, they were substantial, sometimes as much as 22% in magnitude, far greater than anything astronomers had ever expected from a star. While many theories have been proposed, ranging from astronomical phenomena like the presence of a distant planet to the far-fetched idea of an alien megastructure, none have provided a complete explanation. The mystery only deepened when, in September 2019, a new hypothesis emerged, suggesting that the dimming might be caused by fragments of an exomoon. According to this theory, the exomoon was once orbiting a planet in the system, but was torn apart by a catastrophic event, potentially a collision, and now its debris is intermittently passing in front of the star, causing the observed dimming. This hypothesis is just one of many that have attempted to explain the odd behavior of this star. But it's not just Tabby's star that exhibits strange dimming. Other stars known as young stellar objects, YSOs, also experience fluctuations in brightness, but their patterns are quite different from those of Tabby's star. These young stars typically undergo dimming due to the presence of dust and gas in the surrounding nebulae, but the behavior observed in Tabby's star defies these typical explanations. It's the sheer unpredictability of these fluctuations that has kept astronomers on edge, desperately searching for answers. The name Tabby's star itself is a testament to the role of Tabitha S. Boyajian, the American astronomer who led the team that published the paper on the star's irregular light curves in 2015. The star is also commonly known as Boyajian's star, in her honor. One of the more playful monikers for the star, WTF star, comes from the subtitle of the original paper, which was titled "Where's the Flux?" and drew attention to the unexplained dips in brightness. Another nickname, LGM2, references the initial belief that the first discovery of a pulsar in the 1960s was a signal from an extraterrestrial civilization, earning it the nickname LGM1, or Little Green Men. Interestingly, Tabby's star is cataloged in several major astronomical databases, including the Kepler Input Catalog, KIC 8462852, the 2MASS Catalog, and the WISE Catalog. Despite being about 1,470 light-years away from Earth, it remains an object of great fascination. The star itself is located in the northern portion of the sky in the Cygnus constellation, a region home to some of the most iconic stars. It lies between two bright stars, Deneb and Delta Cygni, and while it is relatively close to the star cluster NGC 6866, Tabby's star is not part of that group. With a brightness of about magnitude 11.7, it is not visible to the naked eye, but can be observed with a telescope of at least 5 inches, about 130 millimeters in aperture, assuming the skies are dark and free from light pollution. Tabby's star has been under observation for over a century, with the first recorded sighting dating back to 1890. Since then, it has been included in various catalogs, and astronomers have compiled a wealth of data on its light fluctuations. A large portion of this data comes from the Kepler Space Telescope, which operated from 2009 to 2013. Kepler was designed to detect exoplanets by observing slight variations in the brightness of stars as planets passed in front of them. However, it soon became clear that Kepler had discovered something far stranger than exoplanets. Tabby's star was unlike any other. In 2017, Boyajian and her team reported a particularly significant dimming event, dubbed ELSI. This event, which began in May of that year, was detected by the Las Cumbres Observatory Global Telescope Network, including its telescope in Maui, Hawaii. The event was unique in that it showed a complex, multi-phase dimming pattern similar to a previously observed dip in the Kepler data. Later that year, astronomers detected two more major dimming events named Celeste and Scarab, each one adding more layers of complexity to the mystery. As if this weren't enough to keep astronomers on edge, in September 2017, a major dimming event called Anor began, representing one of the deepest dips recorded. By mid-October, there was even a period of brightness, an anomaly that completely contrasted the usual pattern of dimming. Some speculated that a brown dwarf, a failed star, was passing near Tabby's star, causing the observed fluctuations in brightness. This brown dwarf might have an eccentric orbit, possibly taking over 1,600 days to complete one revolution around the star, which could explain the irregularity of the dimming and brightening. The year 2018 saw even more mysterious dips. By March of that year, a series of dips occurred, with the most significant reaching a depth of over 5%. These dips, though fascinating, also brought up new questions. By 2019, observations from the Transiting Exoplanet Survey satellite, TS, began to provide further insights into the behavior of the star. During this period, a 1.4% dip was observed, among many others, adding more data to the already complex puzzle. One of the most compelling aspects of Tabby star's behavior is how unpredictable its dimming events are. While some stars experience regular dimming as a result of orbiting planets, the behavior of Tabby's star is far more erratic, with dimming events occurring without any clear pattern. This randomness is baffling to astronomers who have considered every possible explanation, from comets and dust clouds to giant structures orbiting the star, yet none of these hypotheses seem to completely fit the data. And so, as astronomers continue to monitor Tabby's star, it remains an enigma. Its fluctuating brightness is a reminder that, even in an age of rapid scientific discovery, the universe still holds secrets that defy our understanding. What causes these fluctuations? What does Tabby's star have in store for us next? Only time and further observation will tell. However, determining the accuracy of the claims about Tabby's star has proven to be an exceptionally challenging task. This complexity arises largely from the reliance on older photographic records, which demand careful adjustments to account for the evolution of astronomical equipment over time. These records, while invaluable, introduce a layer of uncertainty. One study that analyzed the same data suggested that the observed dimming of the star might not be real at all. Instead, it proposed that errors in the data collection or interpretation could be the true cause of the perceived dimming. Another study, drawing from 4 years of data collected by the Kepler Space Telescope, reported that the star had dimmed by roughly 0.34% each year, followed by a drastic 2.5% dip within a short 200-day period in 2017. This sudden, sharp decrease in brightness was unlike anything previously observed, adding to the mystery surrounding the star. After 2017, however, the dimming appeared to return to its slower, more predictable rate. The peculiarities of Tabby's star didn't stop there. In 2018, researchers detected a potential pattern in the dimming events, with a periodicity of 1,574 days, approximately 4.31 years. This suggested the possibility of a recurring, yet still unexplained, cause behind the dimming. But whether this periodicity is a genuine astronomical phenomenon or simply a coincidence remains under scrutiny. The investigation into this curious behavior continued with further developments. In 2021, astronomers made a significant breakthrough by confirming the existence of a red dwarf star in orbit around Tabby's star. This companion star, a small and relatively dim object, was found to be located about 880 astronomical units, AU, away from Tabby's star. To put this distance into perspective, it's about 180 times the distance between Jupiter and our Sun, or roughly 30 times the distance from Neptune to the Sun. In more familiar terms, it's about 5 times the distance to the Voyager 1 spacecraft, which as of January 2025 is the furthest human-made object from Earth. This discovery, though intriguing, didn't immediately provide answers to the dimming mystery, but added an extra layer of complexity to the ongoing investigation. For many years, scientists struggled to explain the strange behavior of Tabby's star, particularly its erratic dimming. Initially, astronomers believed that the brightness variations couldn't be accounted for by typical stellar activity, especially given the star's classification and spectrum. This led to the hypothesis that some external factor might be obscuring the star's light. A variety of potential explanations were suggested, but none of them could fully reconcile with the available data. Some researchers speculated that interstellar dust could be blocking the star's light, while others proposed that the dimming might be caused by enormous planets surrounded by massive rings. Another theory even suggested that the star's system might be undergoing a phase similar to the late heavy bombardment, a chaotic period in the early solar system marked by frequent asteroid impacts. One of the boldest suggestions was that an artificial megastructure, possibly constructed by aliens, could be the culprit. However, in 2017, a shift in thinking came from astronomer Bradley Clare and his colleagues. They argued that the dimming of Tabby's star might not be caused by external factors at all. Instead, they proposed that the star itself could be experiencing internal processes that were affecting how its light was being emitted. More specifically, they suggested that the heat, which would normally escape the star, might be trapped within it, altering its brightness. While this was just one of many ideas under consideration, it marked a significant departure from the search for an external explanation. By 2019, a new theory began to take shape. Astronomers proposed that the dimming could be linked to debris from the destruction of a moon, an exomoon, once orbiting a planet around another star. This moon, they suggested, was shattered, and its fragments were now blocking the light from Tabby's star. While the theory was in its early stages, it presented an intriguing possibility. Around the same time, another group of researchers, using data from several different space observatories, including NASA's Swift Gamma-Ray Burst mission and the Spitzer Space Telescope, concluded that small particles from material around the star might be responsible for the dimming. By October 2017, NASA's official statement was that the star's strange behavior could be attributed to an uneven ring of dust orbiting it, an explanation that seemed to fit with both the long-term and short-term dimming events that amateur astronomers had been observing. Yet, the story didn't end there. Researchers continued to explore the possibility that an object in a highly elliptical orbit, such as a brown dwarf star, might be passing in front of Tabby's star, causing the observed periodic dimming. This hypothesis added another layer of complexity to the already puzzling situation. In the years that followed, astronomers regularly updated the light curves, which document how a star's brightness changes over time. Interestingly, similar fluctuations in brightness were observed in other stars, including a white dwarf, which also displayed unusual light curve patterns. These fluctuations were often attributed to dust debris orbiting the star, further supporting the idea that the dimming of Tabby's star might be caused by material surrounding it rather than by any internal process. One of the more fascinating theories posits that a cloud of disintegrating comets could be orbiting Tabby's star in an elliptical path, similar to the Oort cloud surrounding our own sun. According to this hypothesis, the gravitational influence of a nearby star could have disturbed this comet cloud, sending comets inward toward Tabby's star and temporarily blocking its light as they passed by. However, this theory presents its own challenges. For one, it's unclear whether there are enough comets in orbit to block such a significant portion of the star's light, especially given that up to 22% of the star's light was blocked during the observed dimming events. Further investigations were carried out using submillimeter wavelength observations, which are particularly sensitive to cold dust in the outer reaches of planetary systems, like the Kuiper Belt in our own solar system. These observations suggested that a catastrophic planetary disruption, which would scatter comets and debris into the star's inner system, was unlikely. Nonetheless, the theory of a disrupted asteroid belt remains under consideration, and scientists continue to probe this possibility. Some astronomers, such as Jason T. Wright, have proposed that if Tabby's star is younger than previously thought, based on its position and speed, it could still be in the process of forming planetary material. This could include gas and dust coalescing into planets or other objects. However, studies from the NASA Infrared Telescope Facility and other observatories have found no evidence to support this idea. High-resolution imaging and spectroscopy have also ruled out the possibility of large-scale planetary collisions that could produce enough warm dust to glow in infrared wavelengths. The absence of this glowing dust raises further questions about the potential causes of the star's dimming. Despite these challenges, the theory of planetary debris causing the dimming seems increasingly unlikely, particularly given the rarity of large-scale planetary collisions and the low likelihood of witnessing such events during the Kepler mission's observations. Then, in December 2016, another intriguing hypothesis emerged. A team of researchers proposed that Tabby's star might have consumed an entire planet, which could explain both the temporary brightening caused by the release of gravitational energy as the planet fell into the star, and the subsequent dimming due to the debris left behind in orbit around the star. According to this theory, the destruction of the planet could have caused Tabby's star to briefly brighten about 10,000 years ago, with the dimming observed today representing the star returning to its normal state. In 2017, researchers Suzia and colleagues proposed yet another compelling theory. They suggested that a massive planet, equipped with oscillating rings, could be responsible for the unusual dimming patterns observed in Tabby's star. This theory was one of several attempts to explain the star's erratic light curve. Building on this idea, a team led by Balos further speculated that the large planet could be accompanied by Trojan asteroids, objects that share the planet's orbit located at a specific point called the L5 Lagrangian point. These researchers even went as far as calculating the planet's orbit, predicting that another dimming event could occur in early 2021, followed by another in 2023. Their model suggested that the planet could be up to 4.7 times the size of Jupiter, which would make it a particularly massive planet unless it were still in its infancy. They also proposed that this planet might orbit a red dwarf star about half the size of our Sun. This star would be easier to detect in infrared light, which could provide valuable clues about the nature of Tabby's star and its unusual behavior. Thus, the mystery of Tabby's star continues to evolve, with researchers exploring a wide range of theories, each contributing to the growing complexity of this cosmic puzzle. Existing measurements of radial velocity, which are key to tracking the movement of distant planets, had previously failed to provide enough precision to definitively confirm any particular model about the behavior of Tabby's star. However, new, more accurate data offered a promising breakthrough, narrowing down the range of possible explanations for the star's strange behavior. One such model offered a compelling interpretation of an unusual event, the dramatic dimming of the star that occurred in May of 2017. According to this model, the most likely cause of the dimming was that a planet had passed directly behind the star, temporarily blocking a portion of its light. The model suggested that this obscuration would lead to a temporary decrease in brightness, around 3%, and would last for approximately 2 days, which fit the timing of the May dimming event. If this theory was correct, it further implied that the planet's orbit had a period of roughly 12 years, with a semi-major axis, essentially the average distance between the planet and its star, of about 55.9 astronomical units, AU. This distance is nearly 6 times greater than the distance between Earth and the Sun. The idea that a planet could explain the dimming raised interesting questions about the star and the systems surrounding it, especially in relation to the star's overall behavior during these events. Another fascinating aspect of Tabby's star is the observed redshift, a phenomenon in which light from the star shifts towards the red end of the spectrum. This is often a sign of scattering or absorption by particles such as dust. However, astronomers quickly realized that the redshift wasn't caused by dust obscuring the star. Instead, it seemed to be the result of cooling in the star's outer layers. This cooling could happen if the star's internal heat transport system was disrupted, potentially due to changes in how the star moved heat around within its structure. One of the leading theories suggested that Tabby's star might be transitioning between two different types of heat transport, radiative and convective. This could be linked to the star's extremely strong rotation, which causes different latitudes of the star to rotate at different speeds, leading to complex dynamics in the star's outer layers. Some astronomers even hypothesize that Tabby's star might be exhibiting this unusual behavior because it is approaching a critical point in its evolutionary path, what is often referred to as a phase transition in astrophysical systems. This theory draws on the principles of avalanche statistics, a method used to describe the behavior of complex systems near critical thresholds. As systems approach these tipping points, they often display a peculiar mixture of order and chaos. The fact that other magnetically active stars cataloged in the Kepler Input Catalog show similar phenomena lends some credibility to this hypothesis. Furthermore, some scientists have speculated that the strange behavior of the star could be linked to intense magnetic activity within the star's core. However, another more speculative idea has captured the imagination of many in the scientific community. Some suggest that the dimming of Tabby's star could be caused by a megastructure, a massive construct built by an extraterrestrial civilization. A common suggestion within this theory is that a Dyson swarm, a hypothetical array of satellites designed to collect energy from a star, might be the cause. While this idea is intriguing, not all scientists are convinced. One notable critic, Stein S.E. Goodson, argues that this hypothesis does not offer the most straightforward explanation for the dimming, particularly given the existence of other more plausible theories. Goodson also points out that the alien megastructure theory conflicts with Occam's razor, a principle that favors simpler explanations. Nonetheless, he concedes that the idea is worth exploring, as it remains a testable scientific hypothesis. Despite the many exciting possibilities, it is essential to remember that the notion of extraterrestrial intelligence causing the dimming remains entirely speculative at this stage. In fact, recent studies have largely ruled out the idea that solid objects, such as planets, asteroids, or asteroid swarms, are responsible for the dimming. Similarly, the alien megastructure theory is also looking increasingly unlikely. In 2019, researchers proposed another intriguing possibility, that moons might be to blame for the light curve observed in Tabby's star. By running simulations of gas giant planets with large moons, the researchers found that in half of their simulations, the moons were ejected from their planets. These ejected moons created orbits that produced a light curve remarkably similar to the dimming pattern observed from Tabby's star. As of 2015, astronomers had begun to focus on Tabby's star with heightened interest, hoping to observe another dimming event. With the aid of powerful telescopes equipped with spectrographs, they aimed to study the light from the star in greater detail, hoping to determine whether the objects causing the dimming were solid, like planets, or composed of gas or dust. To this end, a number of sophisticated tools were brought to bear on the mystery. Instruments such as the Green Bank Telescope, the Very Large Array Radio Telescope, and space-based observatories like the Nancy Grace Roman Space Telescope, TESS, and Plato were all enlisted to help shed more light on the phenomenon. In 2016, Tabitha Boyajian, the lead researcher behind the initial study of Tabby's star, launched a crowdfunding campaign to support the ongoing monitoring of the star. The campaign proved to be highly successful, raising over $1.1 million, enough to fund an entire year of continuous observations through the Las Cumbres Observatory Global Telescope Network. Boyajian also collaborated with more than 50 amateur astronomers from the American Association of Variable Star Observers, who contributed by providing nearly continuous coverage of the star. A study published in early 2018 presented an intriguing conclusion. Researchers suggested that whatever was causing the dimming was likely not a solid object, but instead something more diffuse, like space dust. This was inferred from the way the dimming seemed to affect different wavelengths of light, a phenomenon that would be unlikely if an opaque object were blocking the star's light. As such, the idea that dust or another gaseous phenomenon could be responsible gained traction. In December 2018, another wave of studies aimed to investigate more exotic possibilities. The automated Planet Finder telescope was used to scan for unusual laser emissions coming from Tabby's star, which could potentially signal the presence of advanced alien technology. While some intriguing candidates were detected, further analysis confirmed that these signals were coming from Earth, not the star itself. Earlier, in October 2015, the SETI Institute had used the Allen Telescope Array to search for radio signals from potential extraterrestrial civilizations near Tabby's star. After a thorough investigation, they reported no evidence of technology-related signals, effectively ruling out the idea that alien activity was responsible for the dimming. In 2016, yet another observational effort was launched by astronomers using the Veritas Gamma Ray Observatory. The goal of this mission was to search for ultra-fast optical transients, UFOts, which are extremely brief bursts of light from distant astronomical objects. These flashes last only a few nanoseconds and are incredibly faint, requiring highly sensitive techniques to detect them. Using data collected from Tabby's star between 2009 and 2015, researchers examined whether these rapid bursts of light could provide an explanation for the strange behavior observed in the star. The investigation continues to evolve, with astronomers around the world using cutting-edge technology and creative theories to unravel the mystery of Tabby's star. Whether the answer lies in natural astrophysical phenomena, the behavior of exotic celestial objects, or even something entirely unexpected, the quest to understand this star remains one of the most exciting and challenging endeavors in modern astronomy. However, despite all the efforts and advancements in technology, no unusual emissions were found coming from the star during the initial search. The scientific community, still eager for answers, continued their investigations. Then, in May 2017, another search was conducted, this time with a more focused approach. It targeted laser light emissions. The goal was to probe whether there were any signs of artificial signals, potentially indicating advanced technological activity from a distant civilization. Although the team hoped this new method would yield results, once again, no definitive signs of extraterrestrial signals emerged from Tabby's star. Yet the quest for answers did not stop there. In September 2017, a fresh wave of activity arose in the form of a new set of tasks for the SETI at Home project. SETI, which stands for Search for Extraterrestrial Intelligence, is an initiative designed to sift through enormous amounts of data looking for potential signals that could come from alien civilizations. These new tasks were specifically based on a previous radio frequency survey of the regions surrounding Tabby's star. To enhance the effectiveness of this ongoing search, the work units provided to the volunteers of the SETI at Home project were made significantly larger. This change was a key decision because it helped reduce what is known as quantization noise, a form of interference that can obscure data and make it more challenging to discern any potentially important signals. As the world's scientific community focused on Tabby's star, another discovery surfaced, an anomaly around a different star. A young star known as EPIC 24789 2016, along with a handful of other stars, began to show strange light patterns. These patterns were eerily similar to the mysterious dimming behavior seen in Tabby's star, adding another layer of intrigue to the situation. However, the dips in light observed from EPIC 24789 2016 were markedly different in several key ways. First, the dips were much more dramatic, with the star's light dimming far deeper than the fluctuations observed in Tabby's star. Secondly, the dimming episodes in Epoch 24/7/89/2016 occurred over a much shorter time span, in stark contrast to the gradual, years-long dimming seen from Tabby's star. Moreover, this young star was surrounded by a protostellar disk, a swirling disk of gas and dust that forms around a young star, an attribute that Tabby's star did not exhibit. Tabby's star appeared to be a typical F-type star with no such disk, setting the two stars apart and suggesting that the cause of the mysterious dimming could be very different. In another corner of the cosmos, an even more baffling phenomenon was unfolding, one that would become a cornerstone of modern astrophysical mystery. Known as the Great Attractor, this gravitational anomaly lies in the vast expanse of intergalactic space, a region so vast and distant that it defies easy observation and comprehension. The Great Attractor is the central point of an immense gravitational force that pulls galaxies towards it, including our very own Milky Way. It is thought to be the focal point of a collection of approximately 100,000 galaxies spanning across a vast region of space known as the Laniakea supercluster, a term that itself means immense heaven in Hawaiian, reflecting its scale and grandeur. This colossal concentration of mass has an almost unfathomable influence on the movement of galaxies, with some galaxies being drawn towards it at tremendous speeds. Scientists estimate that the Great Attractor contains a mass that could be equivalent to around 10 quadrillion times the mass of our Sun, a truly staggering number. However, despite its immense gravitational force, the Great Attractor remains hidden from direct view, concealed behind an obstacle known as the Zone of Avoidance. This is a region of space obscured by the thick dust and gas of the Milky Way's own galactic plane, which blocks visible light, making it nearly impossible to observe the Great Attractor using traditional optical telescopes. Despite these challenges, scientists have not given up on uncovering the secrets of this elusive cosmic feature. Although the Great Attractor itself remains hidden in plain sight, astronomers have been able to study its effects indirectly. By observing the motion of galaxies and their clusters, researchers have been able to detect the influence of the Great Attractor, even though it cannot be seen directly. All galaxies in the universe are in motion, and on a grand scale, they are drifting apart due to the expansion of the universe, a phenomenon known as the Hubble flow. This is what we expect to see on the cosmic scale, galaxies receding from each other as the universe expands. But in the region around the Great Attractor, something extraordinary is happening. Some galaxies are not just drifting apart, they are being pulled toward it, defying the general trend of expansion. This anomaly, referred to as a peculiar velocity, is measured through the phenomenon of redshift. When an object moves away from an observer, the light it emits stretches, shifting towards the red end of the spectrum. This effect is similar to how the sound of a passing car shifts in pitch. When it comes to galaxies near the Great Attractor, their redshift values are not uniform, indicating that these galaxies are not simply moving away, but are being pulled towards something massive and mysterious. The speed at which these galaxies are accelerating towards the Great Attractor varies. Some galaxies are moving at speeds as high as 700 kilometers per second, while others, curiously, are moving in the opposite direction, a strange sign of the immense gravitational forces at play. The influence of the Great Attractor is so potent that even our own Milky Way is slowly being drawn towards it at a speed of about 600 kilometers per second, a reminder of how tiny our galaxy is in the grand scale of the universe. The Great Attractor was first identified in 1987 by astronomer Alan Dressler, who, along with other scientists, used redshift surveys to detect the peculiar movement of galaxies in the direction of the constellation Centaurus. This data, combined with measurements of galaxy velocities, helped reveal the hidden gravitational force lurking in the heart of our local universe. Despite the great distance and the numerous obstacles to observing it, the influence of the Great Attractor remains a fundamental part of our understanding of the cosmic forces shaping the universe. Scientists continue to unravel its mysteries, hoping that one day we may be able to peer through the dust and gas that obscure it and uncover the true nature of this extraordinary gravitational anomaly. In the 1970s, astronomers first began noticing signs that something was amiss in a distant region of space. By 1973 and again in 1978, early reports suggested an anomaly. The universe's expansion seemed to deviate from its otherwise uniform motion. Galaxies in a specific area were moving in ways that didn't align with the expected cosmic expansion. Something in the distant cosmos appeared to be exerting a gravitational pull, influencing the movement of galaxies. But what that force was remained a mystery. Over the next few years, astronomers worked diligently to pinpoint the source of this mysterious influence. By 1986, they had narrowed the location of this cosmic force to somewhere between 150 million and 250 million light-years away, specifically in the direction of the constellations Triangulum Australe and Norma. It was in this region that astronomers discovered the powerful gravitational pull of the Great Attractor, an enigmatic gravitational anomaly at the center of a vast cosmic structure. At its core lies the Norma Cluster, a massive gathering of galaxies. The Norma Cluster had been identified through X-ray observations, revealing a complex web of galaxies, many of which were old and engaged in violent collisions. These collisions were producing tremendous bursts of energy, including intense radio waves, adding to the intrigue of the region. While the Norma Cluster is the largest and most well-known in this area, it is not alone. As astronomers continued their research, they identified several smaller clusters surrounding the Norma Cluster, including the Pavo 2, Centaurus, Crux, and Sisa clusters. These smaller clusters, together with the Norma Cluster, form part of an enormous cosmic structure known as the Norma Wall, or the Great Attractor Wall. This colossal galactic filament stretches over hundreds of millions of light-years, containing some of the most massive galaxy clusters in the universe. It is a vast, interconnected structure that plays a significant role in the gravitational dynamics of the universe. In the early 1990s, astronomers began to reconsider the true nature of the Great Attractor. A phenomenon called the Malmquist bias was found to be influencing the earlier data. The Malmquist bias is a statistical effect that occurs when more distant galaxies are harder to detect, leading astronomers to overestimate the mass of distant objects. This prompted a reassessment of the Great Attractor's mass, and by 2005, new observations suggested that it was likely only 1/10 as massive as previously believed. These revised findings also introduced a new theory. The motion of the Milky Way might not be solely influenced by the Great Attractor, but also by an even larger structure beyond it. This discovery led to the identification of the Shapley supercluster, a massive region of space located farther beyond the Great Attractor. This supercluster was found to be a key player in the gravitational tug-of-war affecting the Milky Way and its neighbors. Scientists proposed that the Shapley supercluster could be the true source of some of the gravitational effects originally attributed to the Great Attractor. The Great Attractor, it turned out, was not an isolated anomaly, but part of a much larger cosmic structure known as the Laniakea supercluster. The Laniakea supercluster is an immense collection of 4 major galaxy superclusters, including the Virgo and Hydra Centaurus superclusters. It spans an incredible 500 million light-years across, a truly mind-boggling distance. Though not dense enough to be gravitationally bound, the Laniakea supercluster is anchored by the gravitational pull of the Great Attractor, whose influence continues to shape the local motion of galaxies. The motion of galaxies within the Laniakea supercluster converges toward the region around the Norma and Centaurus clusters, where the Great Attractor lies. This reveals that the Great Attractor is not simply a local phenomenon, but part of the grander structure of the universe, influencing the motion of galaxies and the cosmic flow of matter across vast distances. The Great Attractor is a powerful cosmic force, influencing not just our own Milky Way galaxy, but hundreds of thousands of other galaxies as well. For decades, the Great Attractor has remained a cosmic mystery, and despite the challenges in observing it directly, scientists have pieced together a detailed understanding of its effects. From its discovery in the 1980s to the revelation of its true mass in 2005 through X-ray surveys, our understanding of this enigmatic force continues to evolve. As astronomers refine their technology and deepen their observations, new discoveries are likely to emerge, further illuminating the role the Great Attractor plays in the cosmic dance of galaxies. But the Great Attractor is not the only cosmic enigma that has captivated astronomers. Another peculiar phenomenon lies at the opposite end of the spectrum of cosmic structures, the Botez void. Often called the Great Nothing because of its vast emptiness, the Botez void stands as one of the most mysterious and puzzling regions of space. Stretching across an almost incomprehensible distance, the Botez void has fascinated scientists for decades. Its sheer size and emptiness challenge our understanding of the universe itself. To understand this strange void, we must delve into its structure, its discovery, and the profound questions it raises about the formation of the cosmos. The Botez void is a massive spherical region of space located in the direction of the Botez constellation. What makes it so extraordinary is its almost complete lack of galaxies. Compared to similar-sized regions of space, the Botez void contains far fewer galaxies, only about 60. A comparable region elsewhere in the universe would typically contain around 2,000 galaxies. This unusual emptiness has earned the Botez void the nickname the Great Nothing. With a radius of about 62 megaparsecs, or approximately 330 million light-years, the Botez void is enormous. To put this in perspective, light, traveling at a staggering 300,000 kilometers per second, would take about 330 million years to travel from one side of the Botez void to the other. For comparison, the distance from Earth to the Andromeda Galaxy, our closest galactic neighbor, is only about 2.5 million light-years. The Botez void dwarfs this distance, yet its sparsity of galaxies remains astonishing. The Botez void was first discovered in 1981 by astronomer Robert Kirshner, who was conducting a survey of galactic redshifts. Redshift occurs when light from distant objects shifts toward the red end of the spectrum, indicating that those objects are moving away from us. By studying the redshifts of galaxies, Kirshner was able to pinpoint this massive void. Though voids had been identified before, none were as large or as empty as the Botez void. This discovery raised important questions about the structure and evolution of the universe. The center of the Botez void lies approximately 700 million light-years from Earth, a distance that still places it within a region of space that astronomers can study. Its location within the Botez constellation, a large constellation in the northern sky, offers researchers a unique opportunity to probe this cosmic anomaly. The Botez void does not exist in isolation. It is located near the Hercules supercluster, a vast grouping of galaxies that forms part of the near edge of the void. Understanding why the Botez void is so devoid of galaxies has led scientists to propose several theories. One leading idea is that the void resulted from the merging of smaller voids over time. Much like soap bubbles combining to form a larger bubble, smaller voids might have merged, leading to the creation of the Botez void. As these smaller voids merged, the number of galaxies in the region would have decreased, resulting in the vast emptiness we observe today. Both the Great Attractor and the Botez void stand as monumental mysteries in our quest to understand the universe. While the Great Attractor pulls galaxies together in a powerful gravitational embrace, the Botez void remains a vast, empty expanse, challenging our understanding of the cosmos. Together, these phenomena highlight the vast diversity of structures in the universe. From regions of intense gravitational influence to nearly empty voids, each offering new insights into the nature of space, time, and cosmic evolution. The Botez void is not merely an arbitrary gap in the cosmos. It is a crucial and fascinating feature of the universe's large-scale structure. This void is an immense region, largely empty of galaxies, nestled within the fabric of the universe, which itself is made up of galaxies, galaxy clusters, and cosmic voids. Far from being a random anomaly, voids like the Botez void are thought to be natural products of the universe's ongoing evolution. These cosmic voids form as galaxies, and galaxy clusters are gravitationally drawn toward each other. As they clump together, vast stretches of empty space are left in between, where galaxies are scarce or completely absent. Over time, these voids expand further, and the galaxies that once filled them are pulled into more densely populated regions, leaving behind even emptier expanses. Despite being one of the largest voids known to humanity, the Botez void is not entirely devoid of galaxies. A few scattered galaxies still inhabit this enormous space, though their numbers are much lower compared to other regions of the universe. One particularly notable feature within the Bootes void is a roughly tube-shaped region running through its center, which contains a few galaxies. However, even in this more populated section, the concentration of galaxies remains starkly underpopulated compared to the rest of the cosmos. The galaxies within this central tube could be relics from the formation of the void, or they might have been trapped there as the void expanded. The discovery of the Bootes void in the late 20th century raised significant questions about the distribution of galaxies and the overall structure of the universe. Some scientists initially feared that the existence of such a vast emptiness might conflict with established theories about the universe's evolution. However, further research revealed no major inconsistencies between the Bootes void and the widely accepted lambda cold dark matter, lambda CDM model. This model proposes that the universe began in an extraordinarily hot and dense state known as the Big Bang and has been expanding ever since. The Bootes void, in addition to offering insights into the distribution of galaxies, serves as a valuable piece in the puzzle of dark matter and dark energy, two mysterious and unseen components that make up most of the universe's mass and energy. The existence of such a void allows astronomers to probe how these enigmatic substances influence the formation and placement of galaxies. When comparing the Bootes void to another cosmic oddity, the Barnard 68 molecular cloud, the differences are striking. Barnard 68, a dense, cold cloud of gas and dust, completely obscures light from passing through it, creating an almost impenetrable darkness. Unlike the Bootes void, which, despite being sparse, still allows faint light from distant stars to filter through, Barnard 68 lies only 500 light-years away, a minuscule distance in cosmic terms. While Barnard 68 is a physical object that blocks light, the Bootes void is simply an enormous region of space with few galaxies. It is not a physical entity, but a vast emptiness in the universe's large-scale structure. The importance of the Bootes void cannot be overstated. It offers astronomers a unique opportunity to study voids and their role in the universe's large-scale structure. By examining these galactic deserts, researchers can gain insight into the underlying processes that shape galaxy formation and distribution. Additionally, studying such voids challenges our traditional understanding of cosmic patterns, forcing scientists to reconsider just how vast and empty space can truly be. This void also poses intriguing questions about the nature of dark matter and dark energy. As the vast emptiness of the Bootes void pushes our understanding of the cosmos, it simultaneously opens up new avenues for investigating these two elusive phenomena. The Bootes void, like many other voids across the universe, remains an essential piece of the puzzle in understanding how dark matter and dark energy affect the structure and evolution of the universe. While the Bootes void offers an invaluable window into the cosmos, another fascinating phenomenon has captured the curiosity of astronomers: fast radio bursts, FRBs. These intense, brief pulses of radio waves last only a few milliseconds, but are powerful enough to release as much energy as the sun does over the course of 3 days. Despite their immense energy output, the signals that reach Earth are weak, roughly 1,000th as strong as a mobile phone signal received from the moon. The striking disparity between the energy produced and the weakness of the detected signal is one of the many factors that make FRBs so intriguing. The first FRB was detected in 2007 by astronomers Duncan Lorimer and his student David Narkevich while reviewing old pulsar survey data. This discovery, known as the Lorimer burst, marked the beginning of a new era in radio astronomy. Since then, a growing number of FRBs have been identified, some of which appear to repeat, though their patterns are often unpredictable. Notably, a rare FRB, designated FRB 18916, was discovered to repeat in a regular cycle, pulsing every 16.35 days. Although the majority of FRBs detected so far have originated from beyond our galaxy, a significant breakthrough occurred in April 2020 when the first FRB within the Milky Way was detected by the CHIME radio telescope. By June 2021, astronomers had detected over 500 FRBs from deep space in a single year, underscoring how active and widespread this phenomenon is across the universe. As scientists delve deeper into the origins of FRBs, a variety of potential explanations have been put forward. Some suggest that rapidly spinning neutron stars or magnetars could be responsible. Others have proposed that the bursts may originate from black holes or even extraterrestrial civilizations. In 2020, researchers narrowed down the possible causes to include compact object mergers and the formation of magnetars during supernova events. The discovery of repeating FRBs has been particularly important for advancing our understanding of this enigmatic phenomenon. In 2012, astronomers identified the first repeating FRB source, called FRB 121102, located approximately 3 billion light-years away. Further study of this source in 2017 revealed even more about the peculiar nature of FRBs. Another key discovery in 2019 involved the identification of the first host galaxy for a non-repeating FRB, located roughly 1.8 billion light-years away. This galaxy, much more typical compared to the extreme environment of FRB 111102, closely resembles our Milky Way. More discoveries followed in 2020, with astronomers detecting 2 FRBs originating from the same region of the sky as the magnetar SGR 1935 5+2154. These bursts, though less powerful than others, were significant because they provided direct evidence linking magnetars to the generation of some FRBs. By 2021, astronomers had reported hundreds of FRBs emanating from a single system, indicating that these bursts might be more common and diverse than previously thought. In 2024, an international team of astrophysicists conducted a comprehensive study of one of the few persistent FRBs, FRB 22001124A, located about 1.3 billion light-years away. This burst was found to be originating from a binary system where 2 stars closely interact under intense gravitational forces. These forces create a plasma bubble responsible for the continuous radio emissions that characterize persistent FRBs. Since their initial discovery, FRBs have expanded our understanding of the universe, offering tantalizing glimpses into the complex and dynamic processes at play in the distant reaches of space. As we continue to detect more of these bursts and study their origins, the mystery behind them deepens, offering astronomers fresh insights into the forces shaping the universe. However, the locations of known fast radio bursts, FRBs, are influenced by the areas of the sky that are accessible to observatories. Many of the detected FRBs emit radio frequencies around 1,400 MHz, but a few have been detected at lower frequencies ranging between 400 and 800 MHz. The component frequencies of each burst experience delays of varying lengths, depending on the wavelength. This delay is quantified using a value known as the dispersion measure. As a result, the signal from an FRB appears to sweep downward in frequency, with longer wavelengths encountering more delay than shorter ones. To determine the distance to the FRBs that have been observed, scientists have employed an interferometer called UT-MOST. This tool has established a lower limit for the distance to the FRBs it has detected, suggesting that these bursts are located at least 10,000 kilometers away. This distance is significant because it effectively rules out the possibility that the bursts originate from sources on Earth, further reinforcing the theory that FRBs are an astronomical phenomenon. Fast radio bursts are incredibly intense bursts of radio waves that exhibit pulse dispersion measurements greater than 100 parsecs per cubic centimeter, significantly larger than what would be expected from a source located within the Milky Way galaxy. This large dispersion is consistent with the idea that these bursts travel through an ionized plasma, likely in intergalactic space. Additionally, FRBs do not appear to come from any specific direction, suggesting that they are not originating from the plane of our galaxy. This has led scientists to propose that the bursts are likely coming from sources outside our galaxy. Because these bursts are so isolated and unpredictable, scientists have yet to reach a consensus on what could be causing them. As of 2022, no single widely accepted explanation for their origin has emerged. One theory that has gained significant attention is the possibility that magnetars, highly magnetic neutron stars, could be responsible for generating these bursts. These neutron stars possess extremely strong magnetic fields, which could potentially be the catalyst for the rapid, high-energy events that we observe as FRBs. However, the theory behind fast radio bursts, FRBs, and their origins along with several competing ideas, remains under intense investigation. Despite decades of study, scientists have only scratched the surface in terms of fully understanding these enigmatic signals. One crucial discovery has been that the sources of these bursts are incredibly small, likely no larger than a few hundred kilometers across. This conclusion stems from the observation that FRBs last only milliseconds, and given the speed at which they travel, about 300 kilometers per millisecond, or the speed of light, if their origins were larger than about 1,000 kilometers, a much more complex mechanism would be needed to ensure such brief durations. These constraints imply that the bursts come from exceptionally dense, compact sources, yet they remain tantalizingly difficult to pin down. If these bursts do indeed originate from distant regions of space, the amount of energy required to generate such phenomena is likely immense. The puzzle deepened in 2024 when researchers proposed a new method for measuring the size of the emission region associated with these bursts, using a scattering screen located in the host galaxy. Later that same year, data from an earlier burst recorded in 2022, named FB 2022-11022A, revealed that its emission region was smaller than 30,000 kilometers, offering the first direct evidence of how minute and compact these burst sources could be. One prominent theory is that these bursts could arise from the violent collisions of extraordinarily dense objects, such as black holes or neutron stars. Another possibility is that these bursts may be related to gamma ray bursts, GRBs, another high-energy event in space that shares several similarities with FRBs. Some have even suggested that these signals could be signs of an advanced extraterrestrial civilization, interpreting them as technosignatures, a kind of technological signal transmitted across space. This is not a new hypothesis. It echoes the early days of studying regular pulses from distant sources, where such signals were initially suspected to be from alien civilizations, earning the nickname LGM-1, short for Little Green Men. As the investigation into FRBs unfolded, new ideas continued to surface. In 2007, following the discovery of the first FRB, a hypothesis was put forward that these bursts might be related to hyperflares from magnetars, highly magnetized neutron stars known for their intense bursts of energy. By 2015, studies supporting this idea had started to gain traction. The first FRB originating from the Milky Way was identified in 2022, coming from a magnetar known as SGR 1935+2154, which lent further credence to the magnetar hypothesis. Other theories also began to emerge. Some scientists speculated that the bursts could be linked to supernovae, the massive explosions marking the death of stars, while others considered the possibility of blitzars, short-lived, high-energy events involving collapsing neutron stars. In 2014, a radical new idea was proposed that these bursts might be the result of dark matter interacting with neutron stars, causing their magnetospheres to collapse. More wild ideas followed. One theory suggested that FRBs might be triggered by the decay of axion mini-clusters, hypothetical objects composed of the elusive axions, which have yet to be detected. Another possibility revolved around the interaction of cosmic strings, imperfections in space-time itself, interacting with the plasma in the early universe, thereby generating these powerful bursts. By 2016, another hypothesis emerged, proposing that the collapse of magnetospheres around a specific type of black hole, known as a K-Newton black hole, could account for some FRBs, as well as the weak gamma-ray transients observed shortly after the gravitational wave event GW150914. If FRBs were indeed tied to the cataclysmic collapse of black holes, they could also offer the first direct evidence of quantum gravity effects, a groundbreaking discovery in the field of theoretical physics. Another theory proposed in early 2017 suggested that FRBs might be a result of strong magnetic fields near supermassive black holes, which could destabilize a pulse's magnetosphere, releasing vast amounts of energy in the process. One particularly intriguing FRB, FB12102, has been observed to repeat multiple times, sparking numerous hypotheses about its origin. Among these, the phenomenon of superradiance, a process in which large quantum mechanical states produce coherent emissions in environments such as active galactic nuclei, seemed a likely candidate to explain both the high frequency of bursts and their varying intensity profiles. In 2019, astronomers made an important observation. They speculated that non-repeating FRBs, previously thought to be one-time events, might actually be repeaters whose subsequent bursts simply hadn't been detected yet. A key observation from 2022 saw an FRB exhibiting multiple periodic peaks lasting over 3 seconds, suggesting that it might have originated from a neutron star. Fast radio bursts are typically named after the date they were detected, with an alphanumeric designation added to distinguish multiple bursts from the same source. The name of the burst refers to its origin rather than the burst itself, meaning that a single source, such as FB 12112, will continue to be linked to multiple bursts over time. The very first FRB, discovered in 2007, was dubbed the Laura burst, after Duncan Lorimer, who first identified the signal while reviewing old data collected in 2001 by the Parkes Radio Telescope in Australia. The burst was less than 5 milliseconds long and came from a point in the sky about 3 degrees away from the Small Magellanic Cloud. Given its characteristics, it was determined that the burst did not originate from the Milky Way or the Small Magellanic Cloud, leading to its designation as the Laura burst. Current models suggest that this burst came from a location less than 1 gigaparsec away from Earth. No further bursts were detected during 90 hours of additional observation, leading researchers to believe that it was a one-time event, possibly the result of a supernova or the merger of relativistic objects. In 2010, the discovery of a set of 16 similar pulses by the Parkes Radio Telescope appeared to support the theory that these bursts were of terrestrial origin. It turned out that these signals were caused by a microwave oven's magnetron tube when the door was opened during operation. However, a few years later, in 2015, another significant FRB was detected, this time by the Green Bank Telescope, and it revealed some fascinating new characteristics. This burst, FB 11523, was the first in which linear polarization was observed, allowing for measurements of Faraday rotation, the change in the plane of polarized light as it passes through a medium with a strong magnetic field. Scientists estimated that this burst likely originated up to 6 billion light-years away, and studies suggested that as many as 10,000 FRBs might occur every day across the sky. In 2012, another critical discovery was made when FB 121102 was detected by the Arbo Radio Telescope. It confirmed that FRBs were extragalactic in origin, based on a phenomenon called plasma dispersion. In 2015, a researcher named Paul Schultz uncovered an interesting find in previously collected data. In May and June of that year, 10 non-repeating FRBs were discovered, showing characteristics similar to FB 121102. This suggested that they could be emanating from a young, rapidly spinning neutron star, or possibly from a highly magnetized neutron star known as a magnetar. By December 2016, more bursts were detected from the same region of space as FB 11102, confirming that this source was repeating. This observation ruled out the possibility that it originated from a one-time catastrophic event. The location of FB 12102, at least 1,150 astronomical units away from Earth, was far too distant to be a signal from human-made sources, and scientists began to confirm that it was of extragalactic origin. As new data continued to pour in, theories regarding the nature of FB 12102 evolved. In April 2018, a new hypothesis suggested that these bursts might originate from a dwarf galaxy approximately 3 billion light-years away, potentially linked to a low-luminosity active galactic nucleus, or even from an unknown type of extragalactic source. A more radical suggestion was that a young neutron star could be energizing a supernova remnant in that galaxy. By 2017, an important discovery emerged when astronomers detected 15 more repeating bursts from the same region of space, further increasing the mystery of FB 1211102. These bursts exhibited high polarization and underwent Faraday rotation, a phenomenon that had been observed previously. The bursts were linked to a repeating cycle with periods of heightened activity and relative quietness. By 2020, the repeating cycle of FB 12102 had been determined to follow a consistent pattern, active bursts lasting around 90 days, followed by a quieter period of about 67 days. In 2022, over 300 bursts were recorded, adding to the mounting evidence that FB 121102 is one of the most active FRB sources ever discovered. Then, in 2023, further observations revealed the shortest bursts ever recorded, lasting just 5 to 15 microseconds, deepening the ongoing mystery of their origin and nature. The story of fast radio bursts has thus been a journey of discovery and speculation, with each new finding sparking fresh theories and possibilities. These bursts are likely among the most significant astrophysical phenomena of the 21st century, and as technology advances, they may unlock some of the deepest mysteries of our universe. However, the initial assumption that the afterglow was related to the fast radio burst, FRB phenomenon, was soon questioned. By April 2016, further analysis revealed a surprising revelation. The afterglow wasn't connected to the FRB at all. Instead, it was the result of a highly energetic and mysterious phenomenon originating from an active galactic nucleus, AGN. Powered by a supermassive black hole, this AGN was emitting dual jets of energy that created the afterglow. The confusion stemmed from the fact that the afterglow did not behave in the way scientists had expected. It didn't fade away quickly like typical FRB afterglows. This anomaly led researchers to reevaluate their initial assumptions, ultimately concluding that the afterglow was unrelated to the FRB and instead was a product of the AGN's energetic processes. As research into FRBs continued, the upgraded Observatory Synthesis Telescope UST near Canberra, Australia, made an important discovery. In 2015 and 2016, a 3-part survey conducted over 6 months identified 3 additional FRBs. These bursts were detected at a frequency of 843 megahertz, but because they were observed with a relatively narrow beam, their dispersion was not as precise as other observations. Despite this, the discovery added to the growing body of evidence that FRBs were real, albeit puzzling phenomena. In 2017, another significant step forward came with a short survey using part of the Australian Square Kilometre Array Pathfinder, ASCAP. Over the course of just 3 to 4 days, researchers observed a particularly bright FRB known as FRB 1171107. This burst had a fluence of 58 plus or minus 6 Jansky milliseconds, which was notable for its brightness and precision. Researchers Anastasia Fauve and Abraham Loeb speculated that FRBs might be occurring as often as once per second. Although previous studies had not been able to confirm this frequency, the idea sparked further interest in understanding how often these mysterious bursts might occur. The theory prompted additional studies and discussions about the prevalence of FRBs and their potential origins. By March 2018, the Parkes Observatory in Australia reported another breakthrough, the detection of 3 more FRBs, one of which, named FRB 110309, had an astonishingly high signal-to-noise ratio. This FRB reached a remarkable value of 411, a level that set a new benchmark for FRB detection. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, which began operations in September 2018, would also play a crucial role in advancing our understanding of FRBs. While CHIME's primary mission was to observe the hydrogen content across the universe, its secondary objective was to detect FRBs, and it was incredibly successful in this task. One of CHIME's key discoveries was FRB 180725A, which stood out for being the first FRB detected at a frequency below 700 megahertz, reaching as low as 580 megahertz. In October 2018, astronomers reported the discovery of 19 new non-repeating FRBs by the Australian Square Kilometre Array Pathfinder. Among these was a particularly fascinating group, 3 bursts that had smaller dispersion measures than those seen in previous FRBs. This observation hinted at a different class of FRBs, potentially offering clues about the underlying mechanisms driving these bursts. The following year, in January 2019, astronomers announced a groundbreaking discovery, a second repeating FRB source designated FRB 180814. Between August and October of 2018, 6 bursts had been detected from a single location in the sky. This discovery, made during CHIME's pre-commissioning phase, was a major leap forward. It hinted that repeating FRBs might be more common than previously thought, and suggested that CHIME would likely continue to uncover such sources in the future. Amid all these discoveries, the media was abuzz with speculation about the nature of FRBs. Some outlets suggested that the enigmatic signals could be evidence of extraterrestrial intelligence, a notion that had been explored by a few scientists in relation to other FRBs. However, the team responsible for discovering FRB 0814 was quick to dismiss such ideas, sticking to more plausible astrophysical explanations. One of the most significant and intriguing FRB discoveries came in 2019 with the identification of FRB 18-19116. This repeating FRB, discovered by CHIME, was located in a medium-sized spiral galaxy approximately 500 million light-years away, making it the closest FRB ever detected at that time. What set this FRB apart was its regular periodicity. Unlike other FRBs, which were erratic in their occurrence, FRB 18-1916 exhibited a consistent pattern. Bursts would appear in clusters over a period of around 4 days, followed by a dormant phase lasting about 12 days. This cycle repeated every 16 1/3 days, providing a groundbreaking insight into the regularity of these mysterious signals. In February 2020, researchers conducted further studies using several instruments, including the Swift X-ray Telescope, XRT, and the Ultraviolet Optical Telescope, UVO, to better understand the behavior of FRB 18-916. Similar observations were also carried out by the Sardinia Radio Telescope, the Medicina Northern Cross Radio Telescope, and the Galileo Telescope in Asiago. In December 2019, the Chandra X-ray Observatory was used to explore the area around FRB 18-1916, but no significant X-ray emissions were detected from either the FRB's location or its host galaxy. This finding raised important questions about the relationship between FRBs and other forms of electromagnetic radiation. By April 2020, follow-up studies conducted by the Global Master Network provided more data, and their findings were published in the Astronomer's Telegram. Observations continued throughout 2021 with new insights emerging, including the curious case of FRB 18-18-1112. This FRB remained undisturbed despite passing through the halo of an intervening galaxy. The fact that its signal appeared unaffected sparked numerous questions about the mechanisms behind FRBs, as well as the potential role of intervening cosmic structures. Another particularly exciting discovery occurred with FRB 18-18924, which became the first non-repeating FRB to be traced back to its origin. This burst was found to originate from a galaxy located 3.6 billion light-years away, almost as far as the previous record holder, FRB 12-1102, which had been linked to a magnetar, a type of neutron star with an intense magnetic field. What was particularly interesting about FRB 18-18924 was the fact that its host galaxy was older and less active than that of FRB 12-1102. This raised even more questions about the different types of galaxies from which FRBs could originate and the variety of cosmic environments in which these mysterious bursts could occur. The rapidly accumulating discoveries and analyses of FRBs continue to fuel new theories and possibilities, suggesting that we have only begun to scratch the surface in understanding these elusive and perplexing events. However, the galaxy emitting the fast radio burst FRB 1800-8924 was not an active site of star formation. To detect this mysterious burst, astronomers had to conduct a comprehensive and far-reaching survey of the sky. Using a network of 36 telescopes, they meticulously scanned vast stretches of the cosmos. It was only after a concerted effort that the signal was detected. But the story didn't end there. Further observations were required to understand the true nature of the source. This led to the use of some of the most advanced telescopes in the world. Follow-up studies were carried out using the Very Large Telescope located in Chile and the Gemini Observatory, perched on the peaks of Hawaii. The data they gathered revealed critical information about the distance to the source, as well as the characteristics of the host galaxy itself. These revelations then provided astronomers with a unique opportunity to study the composition of the intergalactic medium, the vast, largely invisible matter that exists between galaxies. In June 2019, Russian astronomers made headlines when they reported the detection of 9 FRB events, including FB1, 51125, which marked the discovery of the third repeating FRB ever observed. Through an analysis of archived data collected between July 2012 and December 2018, astronomers traced these signals to the Andromeda Galaxy and the Triangulum Galaxy. The data used in this groundbreaking discovery came from the BSA LPI Large Phased Array Radio Telescope at the Pushchino Radio Astronomy Observatory, adding a significant new layer to our understanding of the origins of these enigmatic bursts. But the discoveries didn't stop there. In May 2019, another FRB caught the attention of astronomers, FB19520. This signal was observed by the 500-meter aperture spherical radio telescope FAST in China and localized with the RealFast system at the Carl G. Jansky Very Large Array VLA. Optical observations were then conducted using the Palomar 200-inch Hale telescope, revealing that the burst originated from a distant dwarf galaxy situated at a redshift of 0.241. What made this particular FRB even more intriguing was the fact that it was the second one to be associated with a persistent radio source, PRS, which signaled that the environment around the source of the burst was dense, magnetized, and highly turbulent. By June 2022, it had been confirmed that FB2952b, a previously detected burst, was also a repeating FRB. In May 2023, astronomers noted multiple bursts coming from FB219052b, suggesting that magnetic fields at the source were reversing, a phenomenon that had never been observed before in such detail. Not all FRBs, however, are repeating. In July 2019, astronomers discovered FB190523, a non-repeating burst that was traced to a region only a few arcseconds in size. This region contained a massive galaxy situated about 8 billion light-years away, with a redshift of 0.66. This discovery was a crucial step forward as it revealed more about the diversity of FRBs and the variety of sources that could give rise to these fleeting signals. In August 2019, the CHIME, Canadian Hydrogen Intensity Mapping Experiment, Fast Radio Burst Collaboration, reported the detection of 8 additional repeating FRB signals. By December of that same year, astronomers from the Australian Telescope National Facility had observed FRB 191223 in the Octans constellation. Just days later, on December 31st, another FRB, FB 191228, was detected in the Pisces Austrinus constellation using the Australian Square Kilometre Array Pathfinder, ASCAP. In early 2022, astronomers proposed that a globular cluster within the M81 galaxy, a grand design spiral galaxy located about 12 million light-years away, might be the source of the repeating FRB 200112E. This discovery further expanded the list of sources tied to repeating FRBs, adding to our growing understanding of these signals. Then, in September 2023, astronomers announced the detection of FB 220317A, one of the faintest FRBs ever discovered. The burst was localized to a specific region in the sky, providing valuable data for future investigations into its origin. One of the most fascinating discoveries came on April 28, 2020, when astronomers from CHIME detected a bright radio burst originating from the galactic magnetar SGR 1935 plus 2154, located around 30,000 light-years away in the Vulpecula constellation. This burst, known as FB 200428, was groundbreaking because it marked the first FRB detected within the Milky Way and was directly linked to a known source, a magnetar. The connection between this local burst and the extragalactic FRBs further supported the hypothesis that magnetars could be responsible for generating these mysterious signals. In January 2024, astronomers reported that the source of FB 220610A was a rare blob-like group of galaxies. This finding added yet another layer to the growing variety of sources associated with FRBs. Meanwhile, on September 24th, 2 more FRBs, FB 20914 and FB 20919, were detected by the Parkes Radio Telescope. Later, upper limits on low-frequency emissions from another FRB, FB 2000N14, were reported by the Square Kilometre Array Radio Telescope project. Throughout 2021, numerous follow-up observations led to the detection of multiple bursts from several repeating FRBs, including FB 220124A. The burst activity was so high that astronomers recorded more than a dozen bursts over the course of the year. Early investigations into FB 20010124a suggested that its source might be a binary system composed of a magnetar and a barar, a type of massive star known for its strong magnetic fields. In April 2021, astronomers detected two new bursts, FB 22101a and FB 22142a, believed to be repetitions of FB 2002-011124a, providing further confirmation of the activity surrounding this repeating FRB. By the end of June 2021, the Observatory Synthesis Telescope, UTMOST, detected another FRB, FB 2163a, linked to a previously known region in the sky. This was yet another significant addition to the expanding catalog of FRBs, showing the increasing complexity and diversity of these signals. All of these discoveries have contributed to the rapid expansion of our understanding of fast radio bursts. From their mysterious origins to the various environments in which they occur, each new observation has provided crucial insights into one of the most exciting and enigmatic areas of modern astronomy. On a much grander scale, dark matter remains one of the biggest mysteries of the universe. Although scientists have strong evidence for its existence, they cannot see, touch, or directly detect it. Dark matter does not interact with light or any other form of energy that we can measure, and yet it is clearly influencing the way galaxies move, the behavior of gravity, and even how light bends around massive objects. These strange effects strongly suggest that there is far more matter in the universe than we can observe. One of the ways we detect dark matter's influence is through the behavior of galaxies. Galaxies spin so rapidly that based on the visible matter alone, they should break apart. But they don't. This implies that some unseen mass is holding them together, likely in the form of dark matter. Another key clue comes from gravitational lensing, when light from distant galaxies bends as it passes through massive objects like galaxy-thers. The way this light bends reveals that there is far more mass present than we can see. Dark matter also plays a critical role in shaping the large-scale structure of the universe. It even seems to have influenced the leftover radiation from the Big Bang, known as the cosmic microwave background, CMB. To describe the makeup of the universe, scientists use a model called lambda cold dark matter, lambda CDM. According to this model, only about 5% of the universe is made up of normal, visible matter, the kind we can see, touch, and interact with, like stars, planets, and ourselves. Around 26.8% of the universe is made up of dark matter, an invisible form of matter that interacts solely through gravity. The remaining 68.2% is attributed to dark energy, a mysterious force that is accelerating the expansion of the universe. In essence, dark matter and dark energy together account for 95% of everything in existence, meaning that everything we can observe, the stars, galaxies, planets, and even ourselves, comprises only a tiny fraction of the universe's total mass. Despite decades of searching, scientists have yet to pinpoint the exact nature of dark matter. Since it does not emit or reflect light, it remains undetectable by traditional means. Yet, its influence on the cosmos is undeniable, and its study continues to be one of the most significant frontiers in modern science. However, based on its behavior, researchers have come to believe that dark matter might be composed of tiny, yet undetected particles. While the exact nature of these particles remains elusive, several hypotheses have emerged over the years, each more fascinating than the last. The leading candidates for these mysterious components include weakly interacting massive particles, or WIMPs. These hypothetical particles are proposed to be heavy, yet interact so weakly with normal matter that they are detectable only through their gravitational effects. Another intriguing possibility is the axion, a light particle that could not only explain dark matter, but may also solve some of the most perplexing questions in particle physics. Additionally, some scientists have speculated that primordial black holes formed in the early universe long before the first stars and galaxies, might be responsible for dark matter. Dark matter is further categorized by the speed of its particles with three main categories: cold, warm, and hot. Most astrophysicists lean toward the idea that dark matter is cold, meaning its particles move slowly. This slow movement allows them to clump together, playing a crucial role in the formation of the universe's large-scale structures over time. Despite the overwhelming evidence pointing to dark matter's existence, there remains a small faction of scientists who propose an alternative explanation. What if our understanding of gravity is incomplete? Instead of searching for invisible matter, could it be that we simply need to modify the laws of gravity? One of the most well-known alternative theories is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently on cosmic scales than it does on smaller scales. Some researchers have gone even further, presenting more radical ideas about gravity that challenge the traditional laws we've long accepted. While these theories are captivating and have sparked intense debate, none of them can fully account for all the observations that dark matter helps to explain. This suggests that even if gravity requires revision, dark matter still plays an essential role in shaping the universe as we know it. The idea of hidden, unseen matter in space isn't new. In fact, it's been around for more than a century, with contributions from some of the brightest minds in science. The earliest inklings of this idea can be traced back to 1884, when British scientist William Thomson, better known as Lord Kelvin, observed the motions of stars around the sun. He found that their movements didn't quite add up unless some invisible mass was influencing them. Though he didn't use the term dark matter, Lord Kelvin's observations laid the groundwork for future inquiries into the nature of the universe. In 1906, French mathematician Henri Poincaré became the first to coin the term dark matter, or matière obscure, obscure matter. He suggested that some of the mass in the universe might be hidden, though he believed it would be less abundant than the visible matter we could already detect. A few decades later, in 1922, Dutch astronomer Jacobus Kapteyn furthered the conversation by proposing that unseen forces might be affecting the motion of stars, hinting that dark matter could be real. But it wasn't until 1930 that Swedish scientist Knut Lundmark made a pivotal observation. The universe appeared to contain far more mass than could be accounted for by visible matter alone. This was a crucial step toward the realization that what we could see with our telescopes represented only a small fraction of the universe's true mass. In 1932, Dutch astronomer Jan Oort expanded on Lundmark's work. He studied the movement of stars in our own galaxy and concluded that there was far more mass than could be accounted for by visible objects. However, some of Oort's measurements were later found to be inaccurate, prompting further research to verify his findings. A year later, in 1933, Swiss astrophysicist Fritz Zwicky made a breakthrough while studying the Coma cluster, a large collection of galaxies. He noticed that the galaxies were moving far faster than expected, based solely on the visible matter. According to the laws of gravity, they should have been flying apart. Yet, something unseen was holding them together. Zwicky estimated that the cluster contained around 400 times more mass than was visible, coining the term Dunkel Materie, or dark matter, to describe this unseen mass. Although his calculations were somewhat inaccurate, Zwicky's concept was on the right track. The universe contained much more mass than we could directly observe. Initially, Zwicky believed that dark matter was simply invisible, normal matter that didn't emit light. It wasn't until much later that researchers began to entertain the possibility that dark matter might be an entirely different substance altogether. Still, Zwicky's work was instrumental in sparking modern research into dark matter. In the years that followed, further evidence began to accumulate. In 1939, astronomer H.W. Babcock studied the rotation of the Andromeda Galaxy and found that the stars on the galaxy's outer edges were moving much faster than expected. This hinted that some unseen force, likely dark matter, was influencing their motion. Then, in 1940, Jan Oort made another significant discovery by observing the galaxy NGC 3115, which appeared to be surrounded by an invisible mass, reinforcing the idea that galaxies might be enveloped in dark matter. As the 20th century progressed, more and more scientists found clues pointing to the existence of dark matter. Advanced telescopes and space observatories continue to explore its effects, yet the true nature of dark matter remains one of the greatest unsolved mysteries of modern science. In the 1970s, dark matter began to capture more widespread attention as various scientific discoveries converged to suggest that galaxies might be surrounded by vast, invisible halos of matter. In 1974, two independent teams, one from Princeton, led by Jeremiah Ostraker, Jim Peebles, and Amos Yahill, and another from Tartu, Estonia, led by John Anastasios N. Sar and A.N.S. Carrick, reached the same conclusion. The theory of dark matter had gained substantial backing. One critical clue that pointed to the existence of these invisible galactic halos was the way galaxies spin. Optical and radio astronomy played pivotal roles in these discoveries. Vera Rubin and Kent Ford, using a newly developed tool called a spectrograph, made precise measurements of how fast the outer edges of spiral galaxies were moving, revealing surprising results in the rotation patterns. Simultaneously, radio astronomers began using advanced radio telescopes to study hydrogen gas at a wavelength of 21 centimeters in nearby galaxies. Unlike starlight, which is concentrated in the central areas of galaxies, hydrogen gas extends much farther out. This enabled astronomers to study rotation speeds at much greater distances, offering a clearer picture of a galaxy's total mass. The early studies of Andromeda, conducted with massive telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen rotation pattern didn't match what would be expected according to Kepler's laws. These laws describe how objects should move around a central mass. As technology advanced, more accurate instruments allowed for deeper, more refined studies. In 1975, researchers Roberts and Whitehurst measured Andromeda's rotation speed as far as 30 kiloparsecs, revealing that the galaxy's rotation curve remained flat even at extreme distances. This was a crucial observation, suggesting that far more mass existed beyond what could be detected by conventional telescopes. Their findings were graphically represented, with one line showing the optical data from stars and another line revealing the total mass of the galaxy, which continued to increase at the galaxy's outer regions. By the late 1970s, most astronomers had come to accept the idea that dark matter halos likely surrounded galaxies, marking one of the most significant and enduring mysteries in space research. The 1980s and 1990s brought even more compelling evidence in support of dark matter. One major study, conducted by Persic, Salucci, and Stell in 1996, examined the rotation curves of 967 spiral galaxies, providing strong evidence for the presence of dark matter. Other signs that pointed to dark matter included gravitational lensing, where galaxy clusters bend light from objects behind them, along with the distribution of hot gas in galaxies and clusters, and small fluctuations in the cosmic microwave background radiation, which is the faint afterglow of the Big Bang. These multiple observations, combined with ongoing research, continue to fuel the search for answers to one of the most profound questions in cosmology: what exactly is dark matter? Today, the scientific community is largely in agreement that dark matter is made up of particles yet to be discovered, particles that are unlike anything we currently understand. These particles are so elusive they have never been directly observed. The search for them has become one of the most complex and exciting challenges in modern physics. Researchers around the world employ a variety of cutting-edge techniques, experiments, and technologies trying to unravel the mystery that is dark matter. At its core, the concept of matter refers to anything in the universe that contributes to the total energy content, and its density decreases in a specific manner as the universe expands. In other words, the farther the universe stretches, the more spread out matter becomes. This is fundamentally different from radiation, which fades away at an even faster rate. Radiation loses energy as the universe grows, following a pattern known as the inverse fourth power of expansion. On the other hand, the cosmological constant, a term in Einstein's equations, behaves in a unique way. It remains constant regardless of the expansion of the universe. No matter how much the universe expands, the energy density of the cosmological constant does not change, which sets it apart from both matter and radiation. This difference in behavior is largely due to something called radiation redshift. To visualize this, imagine the universe expanding. Its size doubles. As a result, the scale factor of expansion also doubles. The energy of phenomena like the cosmic microwave background, CMB, the faint radiation left over from the Big Bang, becomes weaker. This happens because photons, the smallest particles of light, must travel through a larger space, thus losing energy in the process. Similarly, fast-moving particles like early neutrinos lose energy in much the same way. But the cosmological constant, being a property of space itself, remains unaffected by the stretching of the universe, keeping its energy density unchanged. When scientists refer to dark matter, they are talking about components of the universe that cannot be seen directly, but whose mass can be detected through their gravitational influence. These objects obey the same basic rules as normal matter, but they are composed of particles that do not interact with light in the same way as regular matter. As a result, they are invisible to our current observational methods, but their effects are felt throughout the cosmos. Dark matter's exact composition is still a topic of intense debate and research, but one thing is clear. It is crucial to understanding the full structure and behavior of the universe. In a more specific sense, dark matter refers to a special class of invisible matter that is not made up of the usual particles we are familiar with. It's distinct from other forms of missing mass, such as missing baryons, that might account for some of the discrepancies in mass we observe in galaxies and galaxy clusters. Depending on the context, the term dark matter can have slightly different meanings. However, the general idea is that it is some form of unseen mass that profoundly impacts the motion of galaxies and the behavior of large cosmic structures. A fascinating and perplexing piece of evidence comes from the study of spiral galaxies. The arms of these galaxies spin around their centers, and as you move outward from the core, the amount of visible mass decreases. If we could see all the mass in a galaxy, it would act similarly to a simple system, where most of the mass is concentrated at the center, with stars and gas orbiting around it. In such a system, we would expect stars farther from the center to move more slowly, in accordance with Kepler's third law, which governs the orbits of planets in our solar system. The farther a planet is from the sun, the slower it moves. However, this is not what we observe in galaxies. In fact, the rotation speeds of stars and gas in spiral galaxies remain constant, or even increase, as you move away from the center. This unusual behavior suggests that the distribution of mass within spiral galaxies is far from straightforward. To explain this, scientists propose that there may be large amounts of unseen matter, dark matter, on the outer edges of galaxies. These unseen masses exert a gravitational influence, altering the motion of the visible stars and gas in ways we don't fully understand yet. In systems like galaxies, stars also follow a rule called the virial theorem. This principle allows astronomers to infer how mass is distributed within a system based on the velocities of the stars. When studying the movement of stars in systems like elliptical galaxies or dense star clusters, scientists can apply this rule to figure out how mass is spread throughout the system. However, in many cases, the measured speeds of stars do not align with what we'd expect based on the visible mass in the system. Even when we take into account the complex paths stars follow, the observed speeds suggest the presence of additional mass, dark matter, lurking out of sight. Groups of galaxies are particularly valuable when it comes to studying dark matter, as these clusters provide a natural laboratory for exploring its properties. There are three main ways to measure the mass of a galaxy cluster, all of which point to the presence of dark matter. First, astronomers can look at the range of speeds at which galaxies in a cluster move. Second, by studying the X-rays emitted by hot gas within the cluster, they can calculate the temperature and density of the gas. This allows them to estimate the pressure within the cluster, and by balancing that against gravitational forces, infer the total mass of the system. Third, through a technique called gravitational lensing, astronomers can use the bending of light from more distant objects to calculate the mass of a cluster. This method is particularly powerful because it doesn't require direct observation of the galaxies themselves. Instead, it uses the way mass bends light to determine the total mass present in the system. All three of these methods, measuring galaxy speeds, analyzing X-rays, and observing gravitational lensing, consistently lead to the same conclusion. Dark matter makes up about 5 times the mass of all the visible matter in these clusters. This is a staggering amount of mass, much more than what we can directly see, and it is one of the key pieces of evidence for the existence of dark matter. One of the most striking consequences of Einstein's theory of general relativity is the phenomenon of gravitational lensing. This occurs when massive objects like galaxies or galaxy clusters sit between a distant light source and an observer. The gravitational pull of these objects acts like a lens, bending the path of light that passes through them. As a result, light from the distant object appears distorted. The critical point here is that gravitational lensing depends solely on the mass of the intervening object. It doesn't matter what the mass is made of. The more massive the object, the stronger the bending of light. For example, imagine a distant quasar, a bright, distant galaxy behind a cluster of galaxies. The galaxies in the cluster bend the light from the quasar, causing it to appear stretched or distorted. This effect, known as strong lensing, can result in arcs of light that form around the cluster, creating an image of the distant quasar that looks dramatically different from its true shape. By studying the patterns of these arcs, scientists can determine the mass of the galaxy cluster causing the bending. In cases of weak lensing, the effect is much subtler. Instead of forming arcs, the light from background galaxies is only slightly distorted, leading to small changes in the shapes of the galaxies. By carefully analyzing these tiny distortions, astronomers can infer the distribution of dark matter within a galaxy cluster. These observations provide crucial insights into how dark matter is spread across the universe, and the patterns that emerge from these studies match our predictions based on dark matter models. While both dark matter and ordinary matter are types of matter, their behaviors differ drastically. Early in the universe's history, normal matter had an electric charge and interacted strongly with light. This caused it to scatter, making it detectable by telescopes. Dark matter, however, does not interact directly with light, which is why it remains invisible. Despite this, dark matter still exerts a profound influence on the universe. It shapes the structure of the cosmos, affecting everything from the formation of galaxies to the movements of stars within them. One of the most significant ways dark matter affects the universe is through its gravitational pull. It influences the cosmic microwave background, CMB, the faint afterglow of the Big Bang, by pulling on the photons that make up the radiation. This effect is most noticeable on large scales, and it alters the way normal matter behaves. Dark matter's gravitational influence also affects the movement and distribution of normal matter, which is why the two types of matter evolve differently. Normal matter and dark matter leave distinct signatures in the CMB. While the CMB is nearly a perfect black body, meaning it emits radiation with a smooth, uniform temperature, dark matter's gravitational effects introduce subtle variations in the background radiation. These variations provide a crucial piece of the puzzle, allowing scientists to study the early universe and gain deeper insights into the properties of dark matter. Through a combination of observation, theory, and technology, the hunt for dark matter continues. And though much of it remains a mystery, the progress we've made in understanding its effects on the universe brings us one step closer to unlocking its secrets. However, beneath the observable beauty of the universe lies a subtle, enigmatic feature: tiny temperature differences. So minuscule, they seem almost imperceptible to the naked eye. These variations, measuring about 1 part in 100,000, are far from trivial in the world of cosmology. Scientists have long studied these fluctuations, which are known as anisotropies, and mapped them across the expanse of the sky. With advanced tools and techniques, they have translated these irregularities into graphs revealing a profound structure: the angular power spectrum. This spectrum, when examined, reveals a series of peaks. These peaks appear to be evenly spaced, yet they vary in height, offering astronomers vital clues about the very fabric of the universe. The precise positioning of these peaks holds the key to understanding the composition and behavior of the cosmos. By comparing their positions with theoretical models, cosmologists gain deeper insights into the universe's structure and its elusive components. In fact, these small variations, though seemingly minor, provide essential information about the universe's very beginnings, from the nature of its birth to the present day. The first breakthrough in the study of these anisotropies came in 1992 with the launch of the Cosmic Background Explorer, COBE, satellite. Although the resolution of the data was insufficient to reveal the detailed peaks we see today, the discovery was groundbreaking. But it wasn't until the year 2000 that the Boomerang experiment, utilizing a balloon-based telescope, captured the first detailed observations of these peaks. This marked a pivotal moment in cosmology. The subsequent discoveries made by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft provided far more accurate measurements, confirming what many cosmologists had long suspected. The lambda cold dark matter, lambda CDM model of cosmology was indeed a compelling and robust theory. The formation of cosmic structures began shortly after the Big Bang. In the universe's infancy, tiny fluctuations in density, minute variations in how much matter existed in certain regions, set the stage for the cosmos to evolve from a smooth, nearly featureless expanse into the rich, complex structure we observe today, full of stars, galaxies, and clusters of galaxies. In the early moments of the universe's existence, radiation played a crucial role in regulating the density of ordinary matter, preventing these variations from growing into the large-scale structures we now see. Had the universe been composed solely of normal matter, these fluctuations would not have had enough time to coalesce into the galaxies and clusters that dominate the night sky. Here, dark matter enters the story. Unlike ordinary matter, dark matter is not influenced by radiation. This unique property allowed small density fluctuations in dark matter to continue growing, helping to draw normal matter toward these regions of higher density. The gravity of dark matter acted almost like a cosmic magnet, pulling in ordinary matter, which eventually collapsed to form galaxies and larger structures. The role of dark matter in this cosmic dance was vital. It accelerated the process of structure formation, turning a once homogeneous universe into the vast, intricate web of galaxies, stars, and clusters that we now study. A particularly striking demonstration of dark matter's role in shaping the universe can be seen in the Bullet Cluster, an extraordinary collision between two massive galaxy clusters. The Bullet Cluster is particularly important because it offers a direct observation of dark matter's presence through gravitational lensing, the bending of light caused by massive objects. When scientists examined this phenomenon, they noticed a surprising disparity between where the cluster's mass appeared to be, as indicated by gravitational lensing, and where the visible matter, such as gas and stars, was located. This observation is difficult to reconcile with other theories of gravity, which would expect gravitational lensing to occur only around visible matter. However, dark matter's unique properties, its inability to interact with light in the same way ordinary matter does, explain the observation perfectly. When the galaxy clusters collided, the visible gas, which interacts with electromagnetic radiation, was slowed down and cooled by the forces of the collision. On the other hand, dark matter passed through the event unaffected, creating two distinct regions of gravitational lensing. This observation helped cement the idea that dark matter exists in vast quantities, influencing the cosmos in ways that were once inconceivable. Beyond dark matter, astronomers have also relied on a different tool to measure distances across the universe: Type 1a supernovae. These exploding stars, known for their consistent brightness, serve as standard candles for measuring cosmic distances. By observing how dim they appear from Earth, scientists can calculate how far away they are. These supernovae have revealed something surprising. The universe is expanding at an ever-increasing rate. This acceleration, often attributed to a mysterious force known as dark energy, is one of the most profound discoveries of modern cosmology. Another important cosmic phenomenon is the baryon acoustic oscillations, BAO, which refer to the regular density variations in the normal matter, mainly protons and neutrons, that were set in motion by sound waves in the early universe. These sound waves propagated through the dense, hot plasma that filled the universe before atoms had formed. The effects of these sound waves can still be seen today in the cosmic microwave background, CMB, radiation. As the universe expanded, dark matter and normal matter began to clump together, but the remnants of these sound waves can still be observed in the arrangement of galaxies. These oscillations reveal that galaxies tend to be spaced about 147 million light-years apart, a pattern that was predicted in the 1990s and confirmed in 2005 by large galaxy surveys such as the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining data from the CMB and BAO, scientists have gained a clearer understanding of important cosmological values, such as the rate at which the universe is expanding and the total amount of matter it contains. These findings continue to support the lambda CDM model, which remains the leading theory of cosmology today. Large surveys of galaxy redshifts have further expanded our understanding of the universe's large-scale structure. These surveys have created a three-dimensional map of how galaxies are distributed across the universe. However, these maps are not perfect, as the distances we measure are based on the redshift of light from these galaxies. The redshift is influenced by two main factors: the overall expansion of the universe and the peculiar velocity of the galaxies, which is the motion of galaxies relative to the average expansion. In regions known as superclusters, which are large groups of galaxies, the expansion of the universe slows down due to the gravitational pull between the galaxies. Conversely, vast voids, empty regions between galaxy clusters, expand faster than the universe as a whole. This difference in expansion causes intriguing effects in our observations. For example, galaxies in front of a supercluster appear to be moving toward it faster than expected, making their redshift higher than predicted. On the other hand, galaxies located behind a supercluster exhibit a lower redshift than anticipated. This phenomenon, known as the Kaiser effect, was first predicted by cosmologist Nick Kaiser in 1987 and confirmed in 2001 by the 2DF Galaxy Redshift Survey. The observations supported the lambda CDM model, offering further validation of the standard cosmological theory. Another fascinating aspect of cosmology involves the Lyman alpha forest, a series of absorption lines in the spectra of distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength, known as the Lyman alpha transition. Observing the Lyman alpha forest provides astronomers with a powerful tool for testing and refining cosmological models. The results from these observations have aligned closely with the data collected by WMAP, further supporting our current understanding of the universe. Dark matter, though still mysterious, is commonly categorized into three types: cold, warm, and hot. These classifications do not refer to temperature, but instead to the velocity at which particles moved in the early universe. Cold dark matter particles moved slowly, warm particles moved at moderate speeds, and hot dark matter particles moved rapidly. The classification is determined by the free streaming length, FSL, which measures how far a particle could travel due to random motion before the universe's expansion slowed it down. The size of the FSL has profound implications for the structure of the early universe. Particles with a small FSL, like those in cold dark matter, were unable to travel far, leading to the formation of smaller structures such as galaxies. Hot dark matter, on the other hand, would have allowed larger structures like superclusters to form first, before eventually breaking apart into smaller galaxies. Observations of deep field images of the universe show that galaxies formed first, followed by groups and larger clusters of galaxies. This observation strongly suggests that cold dark matter, not hot dark matter, is the dominant form of dark matter in the universe. One of the key reasons for this is that neutrinos, which are considered hot dark matter due to their extremely high velocities, cannot explain the majority of dark matter. Neutrinos, moving almost at the speed of light, would have traveled too far to allow for the formation of the smaller structures necessary for the formation of galaxies. Thus, cold dark matter remains the leading explanation for the mysterious substance that makes up most of the universe's mass. Dark matter is a broad category that refers to matter that doesn't interact with light, or visible matter, except through gravity. This means that dark matter could consist of familiar but elusive objects such as planets, brown dwarfs, red dwarfs, white dwarfs, neutron stars, and even black holes. These objects, known as MACOs, massive compact halo objects, were once thought to make up the majority of dark matter. However, this theory has largely been rejected in favor of other explanations, with strong evidence suggesting that the majority of dark matter is not composed of ordinary visible matter. If it were, we would be able to detect it through its interaction with light. However, the reality of what we observe in the universe today challenges some of the most fundamental ideas we had about its composition. The amount of normal matter, or baryonic matter, essentially the atoms and particles that make up stars, planets, and everything we see around us, is far less than we would expect, based on what we know about the formation of the universe. According to the Big Bang theory, if there were more baryons, the building blocks of regular matter, in the early universe, we should have seen a much higher abundance of elements such as helium, lithium, and other heavier elements. But what we actually observe is a universe where only about 4 to 5% of its total mass is made up of this regular baryonic matter. This discovery has far-reaching implications for our understanding of the cosmos. Larger-scale studies of galaxies and other cosmic structures have shown that the total amount of matter required to maintain the stability of the universe is much higher, closer to 30% of what we currently observe. This suggests that the remaining 95% of the matter is not the regular, visible type of matter we encounter in our daily lives. This missing matter, often referred to as dark matter, is crucial in understanding how galaxies and other cosmic objects interact with one another. Yet, despite its crucial role in the universe's structure, it remains elusive and largely invisible. Further research into dark matter reveals that only a small portion of it seems to take the form of ordinary objects, like small planets or black holes, collectively known as machos, massive compact halo objects. Studies in gravitational microlensing, the bending of light by gravity, have shown that these objects cannot account for most dark matter. The masses of machos fall within a range that excludes nearly all plausible candidates, meaning that the real nature of dark matter must be something entirely different. The cosmic microwave background, CMB, the faint radiation left over from the Big Bang, has provided strong evidence that about 56% of the universe's matter doesn't interact much with light or regular matter, except through gravity. This observation suggests that dark matter is mostly invisible, detectable only through its gravitational effects on other objects in the universe. If baryonic matter, which makes up the familiar world around us, doesn't explain the majority of dark matter, then dark matter must be composed of something else, something fundamentally different. This leads to the possibility that dark matter is made of non-baryonic matter, which is believed to consist of new, mysterious particles or ancient black holes that formed in the earliest moments of the universe. These particles wouldn't have contributed to the formation of elements during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, their presence is inferred mainly from their gravitational effects, such as the bending of light, a phenomenon called weak lensing. One key class of candidates for dark matter are particles known as WIMPs, weakly interacting massive particles. WIMPs are thought to be elementary particles that interact only through gravity and possibly the weak nuclear force, a force responsible for radioactive decay. The theory posits that WIMPs were created in the early universe, just like regular matter. These particles would make up what's known as cold dark matter. And to match the amount of dark matter we observe today, WIMPs would need to annihilate with each other in specific ways. Theoretical models suggest that WIMPs should have masses on the order of 100 gigaelectron volts, GeV, and interact through the electroweak force. This theory, often referred to as the WIMP miracle, has gained considerable attention because it fits neatly with predictions from supersymmetric theories, which extend the standard model of particle physics. Supersymmetry suggests that for every known particle, there exists a heavier partner particle. A stable supersymmetric particle could be an excellent candidate for dark matter. Researchers have been working tirelessly to detect WIMPs, either by looking for the products of their annihilations, such as gamma rays, neutrinos, and cosmic rays, or by trying to directly observe their interactions with atomic nuclei in laboratory experiments, like those conducted at the Large Hadron Collider, LHC. However, by the early 2000s, experiments failed to find strong evidence for supersymmetry, and the results from the LHC cast doubt on the simplest WIMP models. In light of this, other candidates for dark matter have emerged. One such possibility is the axion, a theoretical particle first proposed in 1978 by Frank Wilczek and Steven Weinberg. Initially suggested to resolve a problem in the theory of quantum chromodynamics, QCD, which governs the behavior of quarks and gluons, axions are incredibly light and weakly interact with other particles. This makes them a prime candidate for dark matter. Axions could have been produced in the early universe and, due to their extremely low mass, might explain some of the small-scale issues in the lambda cold dark matter LCDM model, which is the leading cosmological model. Since WIMPs have not been detected, axions have gained increasing attention, particularly as their ultralight nature may explain some of the small-scale mysteries that have remained unresolved in dark matter research. Another intriguing theory involves primordial black holes that may have formed in the very early universe, during a period known as inflation, when the universe expanded rapidly. These black holes could have formed from incredibly dense regions of matter collapsing under their own gravity, even without the death of a star, which is typically the cause of the more familiar stellar black holes. Primordial black holes could have a wide range of masses, from as small as atoms to as large as, or even larger than, stellar black holes. The theory of primordial black holes was first proposed in 1967 by Yakov Zeldovich and Igor Novikov, and later revisited by Stephen Hawking in 1971. The concept quickly gained popularity as a potential explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the physics of black holes is already well understood. General relativity, which explains how gravity works, and black holes themselves, which have been observed through multiple experiments, provide a solid theoretical foundation for this idea. However, the creation of primordial black holes may require special conditions, like unusual cosmic inflation or physics beyond the standard model of particle physics. In 2015, gravitational wave measurements detected the merging of black holes, some of which had masses too large to have formed through the usual stellar collapse process. This sparked renewed interest in primordial black holes as potential dark matter candidates. Yet, when scientists searched for signs of gravitational lensing from medium-sized black holes, objects that could have been dark matter, they found no conclusive evidence. Some researchers suggest that this might be due to incorrect assumptions about the mass of these black holes. Future observations, perhaps with the help of advanced tools like the James Webb Space Telescope, may provide clearer answers to whether primordial black holes could indeed make up a significant portion of dark matter. Despite all the progress in the field, scientists once believed that small primordial black holes might account for a large portion of dark matter. However, the complexity of the evidence and the uncertainty of the data suggest that the true nature of dark matter may still be far more mysterious than we can currently imagine. As we continue to look deeper into the universe, the quest to understand dark matter is far from over, and each discovery only brings more questions to the surface. However, the Voyager 1 spacecraft, which ventured far beyond the reach of the Sun, provided groundbreaking data by measuring the flow of positrons and electrons. To the surprise of scientists, the number of particles detected was far lower than anticipated, and their energy levels were not in alignment with predictions. This unexpected discovery prompted researchers to reevaluate their assumptions about dark matter and led to a startling conclusion. Tiny black holes, once considered a potential explanation for dark matter, are far too rare to account for the mysterious substance. Despite this, the search for dense forms of dark matter continues to captivate scientists, who explore a range of new theories. Some have even proposed ways to cool dark matter in an attempt to unlock its secrets. As of 2018, the puzzle of dark matter remains unsolved. In 2019, further observations of the Andromeda Galaxy revealed no signs of microlensing, an effect that would be expected if tiny black holes were present in the galaxy. This absence cast more doubt on the idea that primordial black holes could be a significant component of dark matter. Nonetheless, there is still a lingering gap in our understanding of the universe, particularly when it comes to a mass range smaller than what we can currently detect using optical microlensing techniques. In this range, primordial black holes could potentially account for all the dark matter in the universe, a possibility that continues to fuel research and debate. If dark matter is indeed composed of particles that barely interact with anything, a crucial question arises. Could these elusive particles form objects like planets, stars, or even black holes? Historically, the answer has been a resounding no, and there are two primary reasons for this. The first is that dark matter particles cannot easily lose energy. Regular matter forms dense objects like stars and planets precisely because it can shed energy in various ways. For example, when particles fall inward under the influence of gravity, they lose energy, allowing them to slow down and condense into stable structures. Dark matter, however, appears to lack this ability to shed energy. It interacts only weakly with other matter, primarily through gravity, and possibly through some very faint interactions, but this is still speculative. Without a mechanism to release energy, dark matter particles that are drawn inward by gravity would simply speed up, heat up, and eventually escape, preventing the formation of compact objects. Moreover, dark matter does not interact in the same diverse ways that regular matter does. While regular matter interacts via multiple fundamental forces, gravity, electromagnetism, and the strong nuclear force, it can form complex structures like atoms, stars, and galaxies. In stars, for instance, particles engage in nuclear fusion, emitting light and neutrinos. However, no such interactions are observed in dark matter beyond gravity, with some hypotheses suggesting weak interactions, but this remains uncertain. Without the ability to engage in these diverse interactions, dark matter is unable to form the same intricate structures that regular matter does. If dark matter is composed of tiny particles, these particles are passing through every square centimeter of Earth millions, if not billions, of times each second, unseen and undetected. Numerous experiments are underway to test this hypothesis. While the most common candidate for dark matter has been WIMPs, weakly interacting massive particles, axions are also receiving growing attention. Notably, projects like the Axion Dark Matter Experiment, ADMX, are working to explore this possibility. Other candidates include heavy particles from a hidden sector that interact with regular matter solely through gravity. There are two primary types of experiments focused on detecting dark matter: direct detection and indirect detection. Direct detection experiments aim to find evidence of dark matter particles scattering off atomic nuclei within a detector. These experiments look for tiny energy shifts, measured in keVs, caused by the interaction between dark matter and regular matter. When dark matter particles collide with an atom, the atom might release energy in the form of light or vibrations, both of which can be detected. To achieve accurate results, these experiments require an environment that is as isolated as possible from external interference, such as cosmic rays. This is why many of these experiments are conducted deep underground, where the Earth's surface provides a shield from cosmic radiation. Prominent underground laboratories include the Stowe Mine, the Sudan Mine, and the Gran Sasso National Laboratory. To detect these faint signals, scientists use two main technologies: cryogenic detectors and noble liquid detectors. Cryogenic detectors measure heat released from particle collisions in materials like germanium, while noble liquid detectors detect light produced when a particle strikes liquids such as xenon or argon. Some of the most prominent experiments in this area include CDMS, CREST-T, xenon, and LUX. These detectors are especially effective at distinguishing dark matter particles from background particles, which primarily scatter off electrons, whereas dark matter particles are believed to scatter off atomic nuclei. Indirect detection experiments, on the other hand, focus on the aftermath of dark matter particles annihilating or decaying. These experiments aim to detect the particles or radiation that are emitted when dark matter interacts with itself. While no direct detection of dark matter has been confirmed thus far, the data gathered from these experiments have narrowed down the potential characteristics of dark matter particles. One particularly interesting observation comes from the Darmani and Dharmalibra teams, who have noted a subtle annual variation in their data. This change is thought to be due to the Earth's motion through the dark matter field, offering a potential clue in the ongoing quest to understand dark matter. Thus, while dark matter remains an elusive and mysterious component of the cosmos, the search for its true nature continues to push the boundaries of scientific exploration. Whether it is the quest for faintly interacting particles or the hunt for the rarest of celestial objects, each discovery, no matter how small, brings us one step closer to unraveling the deepest secrets of the universe. However, some experiments, such as those involving likes and super CDMs, have not observed the same effect, creating confusion within the scientific community. This discrepancy highlights the challenges in understanding the nature of dark matter. While these experiments yield varying results, others have focused on specialized methods designed to track the motion of dark matter particles. These experiments, often based on the solar system's movement around the center of the Milky Way, aim to detect directional sensitivity. In essence, these studies seek to distinguish signals originating from dark matter from the usual background noise that should be spread evenly across space. Notable examples of such experiments include DMPC and drift, which attempt to detect the direction in which dark matter is moving. These studies could offer valuable insights into potential signals, allowing scientists to separate the effects of dark matter from other cosmic phenomena. Indirect detection experiments play another key role in the search for dark matter. These efforts focus on finding the remnants or byproducts that appear when dark matter particles decay or break apart in space. Such processes may release gamma rays or pairs of regular particles and their opposites, antiparticles. The detection of these particles, particularly in regions abundant with dark matter, such as the center of the Milky Way, could provide significant clues. In some cases, dark matter particles might collide and annihilate each other, producing high-energy gamma rays, antiprotons, or positrons. Alternatively, unstable dark matter particles could disintegrate into regular particles or even new exotic particles, which could be detected indirectly through an unexpected surge in gamma rays or other high-energy emissions from places rich in dark matter, like distant galaxies or the core of our own galaxy. Despite these promising possibilities, there are significant hurdles in this approach. Other cosmic phenomena could generate signals similar to those expected from dark matter interactions, which makes it challenging to pinpoint the origin of the signals. To confirm a dark matter discovery, scientists must collect multiple signals from different sources. These multiple detections help rule out the possibility of alternative explanations. Additionally, dark matter particles that pass through celestial bodies, such as the Sun or Earth, may interact with atoms, losing energy in the process. This energy loss could lead to a buildup of dark matter in the centers of these bodies, thereby increasing the likelihood of particle collisions and potential destruction. When these events occur, they could release high-energy neutrinos, a signature that scientists hope will confirm the existence of dark matter composed of WIMPs, weakly interacting massive particles. Instruments such as the Amanda, IceCube, and Antares detectors are actively hunting for these elusive neutrinos. Their goal is to capture the faint signals that could validate the presence of dark matter in these regions. Alongside this effort, the detection of gravitational waves by LIGO in 2015 has opened new avenues for studying dark matter, particularly if it exists as ancient black holes. This discovery offers the possibility of observing dark matter in a completely different way, potentially leading to breakthroughs in understanding its true nature. Several other experiments have made attempts to detect dark matter emissions, including those from particle destruction or decay. One notable example is the Energetic Gamma Ray Experiment Telescope, which in 2008 observed an unusual amount of gamma rays from the Milky Way. Initially, this was thought to be the result of errors in estimating the telescope's sensitivity. However, the Fermi Gamma Ray Space Telescope continued the search and, in 2009, observed an unexpected increase in gamma rays emanating from the galactic center. This could potentially be a signal of dark matter destruction or, alternatively, the result of an undiscovered population of pulsars. A deeper analysis of Fermi's data in 2012 revealed a signal at 130 giga-electron volts from the galactic center, which was speculated to be the product of WIMP annihilation at even higher energies. Ground-based telescopes have also placed limits on the extent of dark matter destruction in small galaxies and galaxy clusters. The Pamela experiment, launched in 2006, detected an unusual excess of positrons, which might be indicative of dark matter or pulsar activity. However, no corresponding increase in antiprotons was observed, making the connection to dark matter somewhat uncertain. Similarly, the alpha magnetic spectrometer, AMS-02, aboard the International Space Station, which began observing in 2013, has detected high-energy cosmic rays that might be related to dark matter destruction. While promising, these findings must be treated with caution until more conclusive evidence emerges. In another approach to understanding dark matter, scientists are working to create it in laboratory settings. The Large Hadron Collider, LHC, offers one such venue, where high-energy proton collisions may give rise to dark matter particles. Since dark matter interacts only weakly with normal matter, it is difficult to detect directly. However, by observing missing energy and momentum from particle collisions, energy that escapes undetected, scientists hope to find indirect evidence of dark matter's existence. The LEP experiment, which uses a similar method but focuses on interactions between dark matter and electrons, also contributes to our understanding of these elusive particles. Still, any discovery made in laboratory experiments must be verified through direct or indirect detection methods to ensure the newly detected particle is indeed dark matter. Despite the ongoing search, dark matter remains elusive. As a result, several alternative theories have been proposed to explain the same cosmic phenomena that dark matter is thought to account for. General relativity, which has been extensively tested on the scale of the solar system, has yet to be conclusively proven on galactic and cosmic scales. Some researchers argue that modifying general relativity could eliminate the need for dark matter altogether. Alternatives such as modified Newtonian dynamics, MOND-D, a relativistic version of MOND, TVS, FR, gravity, negative mass, dark fluid, and entropic gravity offer different frameworks that might explain the observed data. However, one of the major challenges with these alternative theories is that the evidence for dark matter comes from many independent sources. While a single observation could potentially be explained by a modification to general relativity, reconciling all the evidence without invoking dark matter proves exceedingly difficult. Some alternative theories have had limited success in explaining certain observations. For example, a 2016 test of gravitational lensing supported the concept of entropic gravity, and a 2020 measurement lent some credibility to MOND-D. Nonetheless, the majority of astrophysicists continue to believe that while changes to general relativity might explain some of the phenomena, the overall body of evidence strongly supports the existence of dark matter in some form. Another great mystery that continues to perplex cosmologists is dark energy. This enigmatic force is thought to influence the universe on the largest scales. Its primary effect is to accelerate the expansion of the universe. According to the current model of the cosmos, dark energy accounts for 68% of the universe's total energy content. By comparison, dark matter makes up 26%, and ordinary matter constitutes only 5%. Other forms of energy, such as neutrinos and light particles, contribute almost nothing to the overall energy budget. Despite its extremely low density, approximately 7 in 10 billion grams per cubic centimeter, far less than both regular and dark matter, dark energy's influence on the universe is profound. Its effects dominate the cosmic landscape because it is evenly distributed throughout space, controlling the universe's overall energy balance. Scientists first began to suspect the existence of dark energy after studying the light from distant exploding stars, known as supernovae. These stellar explosions, particularly Type Ia supernovae, serve as excellent standard candles for measuring cosmic distances due to their consistent brightness. By comparing the light from these supernovae to their redshift, the degree to which their light is stretched as they move away from Earth, scientists found that the universe's expansion is not slowing down as previously expected. Instead, it is accelerating. This discovery overturned long-held beliefs that the gravitational pull of all the matter in the universe would gradually slow the expansion. Since this finding, numerous independent observations have confirmed the existence of dark energy, though its true nature remains a mystery. Various theories have been proposed to explain dark energy. One possibility is the cosmological constant, suggesting that dark energy is a constant, unchanging force spread uniformly across space. Alternatively, some researchers believe dark energy could be a result of scalar fields, energy sources that evolve over time and vary across different locations in the universe. The concept of quintessence and moduli are examples of such scalar fields. If the cosmological constant is correct, dark energy would remain the same everywhere and at all times. However, if scalar fields exist, dark energy could vary depending on the region and epoch of the universe. Other ideas, such as interacting dark energy and cosmological coupling, propose that dark energy could be influenced by other forces or might interact with gravity in ways not yet understood. The cosmological constant was first introduced by Einstein to make his equations for general relativity consistent with a static, unchanging universe. He believed that the cosmological constant could act as a force to counterbalance gravity, preventing the universe from collapsing under its own weight. Einstein referred to this constant as lambda, and thought of it as a form of negative mass scattered throughout the universe, exerting a repulsive force. Although Einstein later abandoned this idea after discovering the expanding universe, the cosmological constant has since regained significance in modern cosmology as a potential explanation for dark energy. However, scientists quickly discovered that the original idea of a stable, static universe was far from viable. Even the slightest alteration in the size of the universe would send it spiraling into either uncontrollable expansion or perpetual collapse. In Einstein's early model, the universe, though seemingly balanced, was unstable. Any increase in the universe's size would lead to an escalation in vacuum energy, fueling further expansion. On the flip side, if the universe began to shrink, it would only continue contracting, endlessly collapsing in on itself. Einstein himself later admitted that this concept was flawed, calling his earlier model of a static universe his biggest mistake. In the 20th century, new theories began to emerge. Scientists continued to probe deeper into the true nature of the universe. Among these was the notion that empty space might itself contain energy, a form of energy that wouldn't weaken as space itself expanded. In this view, as the universe stretched outward, the energy associated with this vacuum also increased, in turn, accelerating the expansion. This phenomenon, which seemed destined to occur because of the uneven distribution of matter in the universe, set the stage for deeper investigations into cosmic expansion. In 1929, Edwin Hubble's groundbreaking observations shattered the notion of a still, unchanging universe. His discoveries revealed that the universe was not static, but expanding, an insight that would forever alter our understanding of the cosmos. Einstein, who had championed the idea of a fixed universe, was so taken aback by this revelation that he would go on to regret his earlier stance, famously dubbing it a mistake. Fast forward to the 1980s, when Alan Guth and Alexei Starobinsky introduced the theory of cosmic inflation, revolutionizing our understanding of the universe's infancy. They proposed that in the earliest moments after the Big Bang, the universe underwent a rapid, exponential expansion driven by a force similar to what we now understand as dark energy. This inflationary period, characterized by its astonishing speed, is now considered an essential component of modern cosmological models. However, the energy required to fuel such inflation far exceeded what we observe as dark energy today. The connection between dark energy and inflation remains an open question, one that continues to spark intense debate among cosmologists. Despite this uncertainty, the theory of inflation gained widespread acceptance, and as a result, the cosmological constant became somewhat less central in the quest to explain the universe's expansion. In the 1980s and 1990s, cosmologists began to shift their focus toward understanding the makeup of the universe, particularly through models involving cold dark matter, CDM, alongside small amounts of normal matter. These models helped explain many aspects of galaxy formation and large-scale structure in the universe. However, they couldn't account for everything. For instance, they predicted a lower value for the Hubble constant than what was actually measured, and they struggled to explain the clustering of galaxies in vast superclusters. These problems became even more apparent after the discovery in 1992 of small variations in the cosmic microwave background, CMB, by the COBE satellite. These observations led to the development of new models, including the Lambda CDM model, which incorporated the cosmological constant to better explain the structure of the universe. Then, in 1998, something extraordinary happened. Studies of distant supernovae revealed that the universe's expansion was not just continuing, but accelerating. This was the first strong evidence for the existence of dark energy, an unknown force driving the expansion faster and faster. In the years that followed, additional observations confirmed the presence of dark energy. Experiments like Boomerang and Maxima, which studied the cosmic microwave background, found that the total energy of the universe was very close to what is known as the critical density. This discovery provided strong support for the lambda CDM model, which had now become a cornerstone of cosmological research. By 2001, the 2DF Galaxy Redshift Survey found that ordinary matter made up only about 30% of this critical density, with the missing component, dark energy, accounting for the remainder. Data from the WMAP satellite collected between 2003 and 2010 further solidified the lambda CDM model, offering an increasingly detailed picture of the universe's composition and behavior. The term dark energy itself was first coined in 1998 by Michael S. Turner, building on the earlier concept of dark matter, which had been introduced by Fritz Zwicky in the 1930s. To truly understand how the universe is evolving, scientists need highly accurate measurements of its expansion over time and space. One of the key tools for this is general relativity, which allows researchers to determine the universe's rate of expansion by studying its shape. A critical element in this analysis is the cosmological equation of state, a principle that links temperature, pressure, and the combined amounts of matter, energy, and vacuum energy in any given region of space. Measuring the equation of state for dark energy has become one of the most difficult challenges in modern cosmology. When scientists integrate the cosmological constant into the standard model of cosmology, known as the FLRW metric, they arrive at the lambda CDM model. This model, often referred to as the standard model of cosmology, aligns remarkably well with observational data, making it the most widely accepted framework for understanding the universe's structure and expansion. Since 2013, the lambda CDM model has been increasingly validated through more precise studies of the cosmos, including data from the Planck spacecraft and the Supernova Legacy Survey. Early results from the Supernova Legacy Survey suggest that dark energy behaves in a manner consistent with the predictions of Einstein's cosmological constant, with an accuracy of about 10%. Meanwhile, recent findings from the Hubble Space Telescope's Higher Z team suggest that dark energy has been influencing the universe's expansion for at least 9 billion years, well before the universe began accelerating. Yet, despite these remarkable advancements, the true nature of dark energy remains an unsolved mystery and a subject of ongoing research. Dark energy is believed to be remarkably smooth and uniform, filling the vast emptiness of space with an almost imperceptible density. Its mass is so small, about 10 to the power of minus 27 kilograms per cubic meter, that it is nearly impossible to detect in laboratory experiments. Despite its incredibly low density, dark energy makes up roughly 68% of the total energy content of the universe, primarily because it is thought to fill all of space evenly. This makes it a critical factor in how the universe continues to expand. One prominent idea connecting dark energy to another phenomenon is vacuum energy. According to Heisenberg's uncertainty principle, empty space is never truly empty. Instead, it is teeming with fleeting particles and antiparticles that spontaneously appear and vanish. This constant fluctuation in energy is often considered a potential source of dark energy. According to Einstein's theory of relativity, this vacuum energy should have a gravitational effect, adding to the cosmological constant and further accelerating the universe's expansion. This ongoing interplay of forces continues to drive one of the most profound mysteries in modern physics. What exactly is dark energy, and how does it shape the very fabric of our universe? As cosmologists dive deeper into this enigma, the answers could forever alter our understanding of the cosmos, revealing the fundamental forces that govern space, time, and everything in between. The enigma of dark energy, the mysterious force driving the accelerated expansion of the universe, is one of the most perplexing challenges faced by modern cosmology. While the phenomenon itself is well established in observational astronomy, the true nature of dark energy remains elusive, sparking intense debate and investigation among scientists. One of the central issues stems from the discrepancy between the theoretical predictions of vacuum energy, as suggested by quantum field theory, and the actual value observed in the cosmos. Quantum field theory predicts that vacuum energy should be vastly higher than what is observed, creating a fundamental mismatch that scientists are still struggling to resolve. At the heart of this issue lies the concept of negative pressure, a key attribute of dark energy. In the framework of general relativity, pressure behaves similarly to mass in its influence on gravity. Both pressure and mass contribute to the stress-energy tensor, which dictates how matter and energy affect the curvature of spacetime. This is precisely how gravity operates in the context of the universe's expansion. Negative pressure, as associated with dark energy, acts to push the fabric of space itself apart, accelerating the expansion of the universe. If the universe were contracting, this negative pressure would work to slow down its collapse, potentially leading to a stabilization. This phenomenon, often referred to as gravitational repulsion, defies the usual gravitational attraction we observe with matter and leads to a universe that grows ever faster over time. To understand the expansion of the universe, it's useful to examine the three key components that make up everything we observe: matter, radiation, and dark energy. Matter, in all its forms, whether ordinary like stars and planets, or dark matter, which is invisible and detectable only through its gravitational effects, behaves in a particular way as space expands. Specifically, the energy density of matter decreases in proportion to the cube of the expansion factor. In simpler terms, imagine a box filled with particles. If the box doubles in size, the energy of the particles decreases by 8 times, because they are now spread over a much larger volume. This occurs because the box expands in 3 dimensions, which disperses the energy throughout the increasing volume. Radiation, such as light and heat, behaves in an even more extreme way. As the universe expands, not only does radiation spread out over a larger area, but its wavelength also stretches. This phenomenon, known as redshift, causes radiation to lose energy even faster than matter as space grows. In contrast, dark energy exhibits a fundamentally different behavior. Unlike matter or radiation, dark energy does not dilute as space expands. It is an intrinsic property of space itself, persisting at a constant energy density regardless of the size of the universe. This enduring force is the key to understanding the universe's accelerated expansion. The evidence for dark energy, although indirect, is compelling. One of the primary sources of this evidence comes from observations of the universe's expansion rate, particularly through measurements of redshift and distance. By studying the light emitted by distant objects and how much it is stretched due to the expansion of the universe, scientists have determined that the universe is expanding at an increasingly faster rate as time progresses. This acceleration hints at the presence of a force that has grown in influence over time: dark energy. In particular, the work done by astronomers in the late 1990s, such as the High Z Supernova Search Team and the Supernova Cosmology Project, found that Type Ia supernova, the explosive deaths of stars, were dimmer than expected, indicating that the universe's expansion had sped up, not slowed down. These groundbreaking discoveries were recognized with the Nobel Prize in Physics in 2011, and since then, additional evidence has supported this conclusion, including measurements from the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. Yet, despite the accumulating evidence, some critics argue that the case for dark energy is still not fully conclusive. While redshift and distance measurements are strong indicators, other observations, such as patterns in the CMB, also suggest a universe that is expanding faster than it would without dark energy. Supernovae, for example, are invaluable tools for studying cosmic expansion because their known luminosity allows astronomers to gauge their distance accurately. By measuring how far away a supernova is and how much its light has shifted, scientists can determine how fast the universe is expanding. Recent measurements suggest that dark energy accounts for roughly 71% of the universe's total energy content, with dark matter and ordinary matter making up the remaining 29%. This theoretical breakdown is supported by models that describe how galaxies, stars, and other structures formed over time. The idea that ordinary matter contributes only about 30% to the universe's critical density, what is necessary for the universe to be flat, was further bolstered by findings such as those from the Wiggles Galaxy Survey in 2011. This study, which mapped the distances to over 200,000 galaxies, confirmed that the universe has been expanding at an accelerating rate over time, lending further support to the notion of cosmic acceleration and dark energy's central role in it. In 2011, the Wilkinson Microwave Anisotropy Probe, WMAP, found that dark energy made up around 73% of the universe's total energy content, with the remainder split between dark matter and normal matter. More recent data from the Planck spacecraft slightly adjusted this figure to 68% for dark energy, 27% for dark matter, and 5% for ordinary matter. This updated understanding aligns well with predictions made by the lambda cold dark matter, lambda CDM model, which is the current standard model of cosmology. Dark energy also helps explain certain anomalies observed in the cosmic microwave background radiation. As photons travel through regions of strong gravitational fields, such as those near galaxy clusters, they lose energy, which leads to variation in the temperature of the background radiation. This phenomenon, known as the integrated Sachs-Wolfe ISW effect, provides another crucial piece of evidence for the presence of dark energy. Looking to the future, scientists are using more advanced methods to measure dark energy, such as studying the Hubble constant, which tracks the rate of the universe's expansion over time. By observing galaxies that have passively evolved, acting as cosmic clocks, astronomers can directly estimate how fast the universe has expanded at various points in its history. This ongoing research aims to further refine our understanding of dark energy and its role in the evolution of the cosmos. Despite the growing body of evidence, the true nature of dark energy remains one of the greatest mysteries in modern physics. There are multiple competing theories about what dark energy could be. Some physicists propose that dark energy is a fixed force embedded in the fabric of space itself, known as the cosmological constant. This idea, first introduced by Albert Einstein in 1917 and later revived in the lambda CDM model, suggests that vacuum energy is a fundamental property of empty space. However, quantum field theory predicts that the vacuum energy should be vastly greater than what is observed, creating a paradox known as the vacuum energy problem. If the quantum prediction were true, the universe would have expanded far too rapidly for galaxies, stars, and planets to form. Alternatively, some physicists hypothesize that dark energy is not a constant force but a dynamic field that changes across space and time. This theory, known as quintessence, proposes that dark energy behaves more like a field capable of evolving and influencing the expansion of the universe in a more flexible manner. Quintessence differs from the cosmological constant in that its energy density can vary depending on location and time. Some models of quintessence suggest that the universe's expansion might have been slightly slower than predicted by the cosmological constant, but to date, no definitive evidence has been found to support or disprove this idea. One of the most profound questions surrounding dark energy is why it emerged as the dominant force in the universe at the specific moment we observe. If the universe's expansion had accelerated too early, galaxies might not have had time to form, and life, at least as we know it, could never have arisen. Some cosmologists argue that this is merely a coincidence, an inevitable result of the laws of physics as they stand. Others, however, point to the anthropic principle, which posits that the universe must be as it is because we exist to observe it. This idea suggests that the specific conditions necessary for life to emerge may not be unique to our universe, but we can only observe the one that fits those conditions. Ultimately, while dark energy remains a great cosmic puzzle, it also represents one of the most exciting frontiers in science today. As researchers continue to probe the mysteries of the universe's expansion, they may uncover answers that not only redefine our understanding of the cosmos, but also change our fundamental understanding of the laws of physics. However, certain models of quintessence propose a refined and elegant framework, introducing a tracker mechanism that naturally aligns the dominance of dark energy with the density of radiation during the universe's infancy. These models offer a compelling explanation for how dark energy might evolve and interact with the other forces in the cosmos. Yet, as our understanding deepens, more extreme versions of quintessence introduce even more bizarre and unfamiliar possibilities, pushing the limits of our cosmic imagination. One of the most unsettling variants, called phantom energy, suggests that dark energy may not simply remain constant, but could instead intensify over time. If this scenario is accurate, the universe's expansion would no longer merely persist, but would accelerate uncontrollably, driving the cosmos toward an eventual and catastrophic event known as the Big Rip. This grim fate would unfold in a chilling cascade of events. First, galaxies would begin to pull apart, each one torn from the others by the relentless expansion. Next, individual solar systems would unravel as the gravitational bonds holding planets to their stars falter, and planets would drift away, disassociated from their suns. Eventually, even the very fabric of matter itself would be torn asunder, as the force of expansion pushes the universe toward infinity, shredding atoms into their most fundamental components. In this scenario, everything, galaxies, stars, planets, even the very structure of space-time, would be irreparably destroyed. Even more peculiar is another exotic theory known as K-essence. This hypothesis explores unusual forms of energy that defy the typical laws of physics. In some versions of K-essence, negative kinetic energy is introduced, a strange and counterintuitive concept that could yield unpredictable and potentially chaotic consequences for the evolution of the universe. Unlike phantom energy, which steadily grows stronger over time, K-essence might fluctuate in entirely unexpected ways, making the fate of the cosmos even more uncertain and unpredictable. Recent advancements in observational cosmology have raised new questions, especially regarding discrepancies in measurements of the universe's expansion rate, a phenomenon dubbed the Hubble tension. This mismatch in data has sparked intense debate among researchers. Some believe that this inconsistency could signal the need for new models of quintessence, ones that incorporate additional forces or interactions to account for the observed behavior. If this is the case, dark energy might be far more complex than we have previously imagined, and its true nature may transcend even Einstein's equations. Despite these tantalizing theories, our understanding of dark energy remains firmly tied to the framework of general relativity. Some scientists propose that if we modified general relativity in specific ways, we might be able to explain the universe's accelerating expansion without invoking dark energy at all. While these alternative theories are intriguing, they have yet to match the precision and predictive power of the standard dark energy model. In fact, a critical breakthrough, the detection of gravitational waves from the event known as G71817, has already ruled out many alternative gravity theories. As astrophysicist Ethan Siegel notes, although alternative models make for fascinating academic exercises, the overwhelming consensus among experts is that dark energy is real and integral to our understanding of the universe. No competing theory has yet been able to offer a more accurate description of the data we observe. According to current cosmological estimates, the expansion of the universe began to accelerate approximately 5 billion years ago. Prior to that, the combined gravitational pull of dark matter and regular matter acted as a cosmic brake, slowing the expansion. However, as the universe continued to expand, dark matter began to dilute, weakening its influence on cosmic dynamics. In contrast, dark energy remained largely unaffected, its repulsive force gradually overtaking gravity's pull and pushing the universe into an era of unchecked acceleration. For every doubling in the universe's size, the density of dark matter per unit of space is halved, while dark energy remains nearly constant. This stark contrast in behavior has profound implications for the fate of the cosmos. The true fate of the universe hinges entirely on the nature of dark energy. If it remains constant, as proposed in the cosmological constant model, the universe will continue to expand indefinitely. Galaxies beyond our local group will recede at ever-increasing speeds, eventually surpassing the speed of light, not in violation of Einstein's theory of relativity, but because space itself is stretching faster than light can travel. While some of these distant galaxies might still send signals that eventually reach us, over time the expansion will create a cosmic event horizon, a boundary beyond which no light, no matter how long we wait, will ever reach us. Current estimates suggest this cosmic event horizon lies roughly 16 billion light years away. Any event occurring within this distance could still send light to us, but anything beyond this limit will forever remain out of our observational reach. As galaxies approach this boundary, their light will be stretched into longer and longer wavelengths, eventually shifting beyond the visible spectrum and fading into complete darkness. From our vantage point, the universe beyond our local group will dissolve into a void, with only a few scattered galaxies remaining in an otherwise empty, dark expanse. Over the course of trillions of years, our own local group of galaxies will remain gravitationally bound, but the energy within it will gradually disperse, leading to a state of maximum entropy, a phenomenon known as the heat death of the universe. In this scenario, all available energy will be evenly distributed throughout space, leaving no gradients or differences to drive physical processes. This marks the final stage in the universe's evolution, where no further work can be done, and life as we understand it would cease. It closely resembles a fate once predicted for a matter-dominated universe, before the discovery of cosmic acceleration reshaped our conception of cosmic evolution. Yet, even this dark and desolate vision is not the only possible future. Alternative models, including those driven by the concept of phantom energy, predict a far more dramatic fate. In these scenarios, dark energy intensifies to such an extent that it overwhelms all the fundamental forces of nature. The result is a terrifying big rip where even the most resilient structures, from galaxy clusters to individual atoms, are torn apart as dark energy's influence grows exponentially. In contrast, some models suggest that dark energy may not be permanent, but could evolve over time. If this is the case, cosmic acceleration might eventually give way to a new phase of contraction, leading to a catastrophic event known as the Big Crunch. In this scenario, the universe would collapse back into a singularity, marking the end of the current cosmic era. Even more intriguing is the possibility that dark energy operates in a cyclic manner, driving the cosmos through endless cycles of expansion and collapse. In this view, each Big Bang marks the beginning of a new cosmic epoch, a cycle of birth, death, and rebirth that continues ad infinitum. Far beyond the confines of our solar system lies a planet known as HD 18973b, an exoplanet that challenges everything we think we know about habitable worlds. From a distance, it appears captivating, its rich blue color evoking images of Earth's oceans. However, beneath this striking appearance lies one of the most hostile environments discovered to date. HD 18973b is located about 63 light-years from Earth, and it is far from serene. Instead, it is a place of extreme violence and inhospitable conditions, where the very elements seem to defy what we understand about the rules of nature. Winds on HD 18973b rage at speeds exceeding 2,000 miles per hour. To put this into perspective, the strongest winds on Earth, those produced by the most powerful hurricanes and tornadoes, top out at around 200 miles per hour. The winds on this distant planet are 10 times stronger than anything humanity has ever experienced. But these gales are not simply fast. They are laden with deadly silicate dust and glass particles, turning the atmosphere into a lethal storm of tiny, razor-sharp shards. The planet's extreme conditions are largely due to its close orbit around its host star. HD 18973b is classified as a hot Jupiter, a gas giant similar to Jupiter in composition, but it orbits its star at an incredibly close distance. This proximity results in temperatures that soar above 2,000 degrees Fahrenheit, hot enough to melt many metals. Meanwhile, the night side of the planet, though slightly cooler, still experiences extreme and rapid temperature shifts. The stark contrast between day and night creates a volatile atmosphere that fuels the planet's devastating storms. Perhaps the most astonishing feature of HD 18973b is its rain, though it is nothing like the liquid water rain we experience on Earth. On this planet, the intense heat and pressure cause the silicate particles in the atmosphere to condense into solid form, resulting in glass rain. Instead of the familiar gentle fall of water droplets, the atmosphere releases sharp, molten glass shards, pelting the planet's surface in a deadly, unrelenting downpour. This alien weather system represents the extreme and often violent forces at play in the universe, reminding us of just how chaotic and dangerous the cosmos can be. However, when particles on the alien world of HD 1897333b enter cooler regions, they undergo a dramatic transformation. The intense heat of the atmosphere causes these particles to condense and crystallize into tiny, sharp, solid shards of silicate, essentially minute pieces of glass. As these glass particles are carried by the planet's violent winds, they hurtle through the air with devastating force. Over time, these microscopic fragments fall back toward the surface, creating a phenomenon unlike anything seen on Earth, a deadly, high-speed rainstorm of glass. Imagine for a moment standing in the midst of this storm, not with water droplets falling around you, but with sharp, jagged pieces of glass slashing through the air at speeds exceeding thousands of miles per hour. These shards, propelled by hurricane-force winds, can slice through virtually anything in their path. The sheer violence of the environment makes survival on this planet impossible. No human, spacecraft, or technology of any kind could endure such conditions. If, by some unimaginable stroke of luck, a human were able to visit HD 197733b without protective gear, their experience would be brief, marked by agonizing pain and certain death. The brutal conditions would claim their life in an instant, in a multitude of gruesome ways. The extreme heat of over 2,000 degrees Fahrenheit would immediately inflict severe burns on exposed skin, likely vaporizing any tissue in seconds. The relentless winds, tearing through the atmosphere at incomprehensible speeds, would be more than enough to rip apart any human body or object caught in their grasp. Meanwhile, the razor-sharp silicate shards, falling like deadly rain, would act like a relentless, high-speed hailstorm. Even a single shard traveling at such speeds could be fatal. Nothing on Earth, no material, no suit, no technology, could possibly withstand the combined fury of the heat, the wind, and the rain of glass. HD 189733b is one of the most extreme and inhospitable worlds ever discovered. It is not just a planet, it is an environment where survival is a concept so alien, it's inconceivable. The forces shaping this world, its blistering heat, its ferocious winds, and its atmosphere thick with microscopic glass particles, make it one of the most deadly exoplanets known to science. Orbiting incredibly close to its star, this planet is bombarded by an immense amount of energy. This proximity causes daytime temperatures to soar to nearly 2,000 degrees Fahrenheit, hot enough to melt most metals and making the very air itself violently expand. This sudden expansion creates powerful atmospheric disturbances. Meanwhile, the night side of HD 1899733b, locked in eternal darkness due to the planet's tidal locking with its star, remains much cooler. The stark contrast between the blistering heat of the day and the cooler night generates intense pressure differences, creating winds that reach speeds well over 2,000 miles per hour. These hurricane-force winds are nearly 3 times faster than the speed of sound on Earth, making them capable of carrying massive amounts of silicate particles through the atmosphere. As the winds rush across the surface, they transform the planet's weather into a deadly spectacle, tearing through the atmosphere with such force that they could reduce anything in their path to rubble. One of the most terrifying aspects of HD 18973b is its glass rain. The planet's atmosphere is filled with clouds that contain high concentrations of silicate particles. As these particles cool and condense, they form tiny glass-like droplets. However, unlike the gentle rainstorms we experience on Earth, these droplets are not falling quietly from the sky. Instead, they are driven sideways by winds gusting at speeds of over 2,000 miles per hour, creating a constant barrage of cutting, high-speed glass rain. It's a phenomenon that gives the planet its eerie blue appearance, beautiful from a distance but a deadly trap up close. The extreme weather conditions on HD 1899733b result not only from the planet's blistering heat and howling winds, but also from a chaotic atmosphere that is constantly in motion. Storms form and dissipate with astonishing speed, fueled by the intense heat, rapid planetary rotation, and complex chemical reactions taking place in the atmosphere. These combined factors create an environment that is as unpredictable as it is lethal. The planet's inhospitable nature makes it unlike anything in our solar system or beyond, a world shaped by forces so powerful that even the most advanced technologies would be no match for its wrath. HD 189733b is a massive world, orbiting its star at an incredibly close distance, which exposes it to intense radiation and heat. Because of this proximity, the planet absorbs an immense amount of energy, resulting in an environment that is simultaneously violent and unforgiving. The planet's surface is a relentless battlefield where extreme temperatures and hurricane-force winds dominate the landscape, creating a world where survival seems not only impossible, but absurd. One of the most defining characteristics of this world is that it is tidally locked. This means that one hemisphere of the planet is perpetually facing its star, while the other side is lost in eternal night. This tidal locking creates an extreme imbalance between the day and night sides of the planet. On the day side, temperatures soar to nearly 2,000 degrees Fahrenheit, while the night side remains much cooler, but still far from habitable. The sharp contrast between these two hemispheres fuels a cycle of chaotic, high-speed winds and violent storms that make the planet one of the most hostile environments in the known universe. The day side of HD 189733b is a vast, scorching wasteland. The relentless heat from the star fuels massive atmospheric disturbances, causing the gases in the atmosphere to heat up rapidly and expand. This expansion creates violent pressure variations, which in turn generate hurricane-like winds that scream across the planet at incomprehensible speeds. These winds are far beyond anything we could imagine on Earth, with the power to rip apart anything in their path. Yet, the planet's weather is not just extreme, it is terrifying. On Earth, we are familiar with rainstorms, where water falls from the sky. But on HD 189733b, the rain is composed of liquid glass, a phenomenon that is both awe-inspiring and deadly. The extreme temperatures and powerful winds cause silicate particles in the atmosphere to condense into tiny glass shards, which then rain down from the sky at breakneck speeds. It's a terrifying spectacle, one that could easily destroy anything caught in its path. Standing on the surface of HD 18973b during one of these storms would be nothing short of a nightmare. The sky would be a swirling mix of deep blues and shifting shadows, illuminated only by the light of the planet's distant star filtering through thick clouds laden with silicate particles. The atmosphere would be thick with mist, refracting the light in dazzling, almost mesmerizing patterns. But beneath this beauty lies the deadly reality of the planet's environment. A world where no one, no matter how advanced their technology, could hope to survive for long. The beauty of the scene, as imagined from afar, is utterly deceiving. On the surface of this alien world, there's a false sense of serenity, a deadly illusion of calm. The glass rain that falls across the planet's surface does not drift down like the gentle snowflakes we know on Earth. Instead, it descends with a ferocious intensity, plummeting from the sky at speeds that far exceed several hundred miles per hour. These fragments, razor-sharp and unforgiving, tear through anything they touch, rendering survival on this hostile world virtually impossible. The winds, howling at speeds similar to the most powerful hurricanes, only amplify the peril. Instead of merely falling to the ground, these glass shards are swept by violent air currents, caught in the storm's cyclical motion. The atmosphere of the planet becomes a living, breathing vortex of deadly debris, a swirling tempest that violently churns across the skies. The planet itself seems to be alive, its surface and sky an eternal battleground between heat, wind, and pressure. The silicate particles suspended in the air catch the light of the planet's burning sun, casting an eerie glow that transforms the sky into a macabre painting. Standing on such a world would be overwhelming, to say the least. The sky would seem to be constantly in motion, a relentless force of destruction and chaos. It would be hard to distinguish where the sky ends and the storm begins, as the entire atmosphere becomes a maelstrom of silicate shards, blinding in their intensity, ever threatening. Despite the unimaginable conditions on this exoplanet, HD 189733b has not gone unnoticed by the scientific community. Thanks to advanced astronomical techniques, researchers have found ways to study this far-off world, a place so remote and inhospitable that visiting is impossible, at least for now. For astronomers, the study of such planets has become a vital part of understanding the broader universe. One of the most crucial tools used to study worlds like HD 189733b is spectroscopy. This technique, which breaks down light into its constituent wavelengths, allows scientists to probe the composition of a planet's atmosphere without ever having to physically reach it. By observing how light from the planet's host star passes through the planet's thick, turbulent atmosphere, astronomers can deduce a wealth of information. Spectroscopic data from HD 189733b, for example, has revealed the presence of silicate particles in the atmosphere, an essential clue in identifying the phenomenon of glass rain that characterizes this world. Space telescopes such as the Hubble Space Telescope and the more recent James Webb Space Telescope have proven invaluable in unlocking the secrets of this distant planet. By carefully observing how HD 189733b moves in front of its star, a process known as a transit, scientists can analyze subtle changes in the light as it filters through the atmosphere. These observations give crucial insight into the properties of the planet's weather systems, temperature variations, and atmospheric chemistry. In fact, HD 189733b's atmosphere, filled with these deadly silicate particles, was the first clear evidence of glass rain in an exoplanetary system. Beyond direct observation, scientists also rely on powerful computer simulations to model the extreme conditions of planets like HD 9733b. By feeding real-world data into these simulations, they can predict weather patterns, wind speeds, and temperature fluctuations. These models allow astronomers to better understand how such an extreme and hostile environment might function and how the planet's weather systems interact with its atmosphere. Researchers can recreate the storms, heat distributions, and chemical compositions of HD 189733b, gaining insights into how the planet's extreme conditions might evolve over time. But the study of HD 189733b is more than just an academic exercise in understanding a single alien world. It is a broader exploration that seeks to expand our knowledge of the universe. The study of planets like this helps us realize that the diversity of worlds beyond our solar system is far greater and more extreme than we could have ever imagined. It reveals the complexity of planetary environments and the ways in which they differ from Earth. Moreover, it informs scientists' search for potentially habitable planets. By examining some of the most uninhabitable and hostile worlds, researchers gain a deeper understanding of what makes a planet truly capable of supporting life. Though HD 189733b itself is a nightmarish landscape of searing heat, violent storms, and fatal glass rain, the methods used to study it hold great promise for the future. They may one day guide us to planets that are more like Earth, planets where life, as we understand it, could thrive. In the vastness of the cosmos, where the conditions on other planets can seem alien and hostile, HD 9973b serves as both a warning and a testament to the raw power of nature. It is a world where forces of heat, wind, and pressure collide in an unyielding struggle, creating an environment that is as awe-inspiring as it is terrifying. The study of exoplanets such as HD 189733b fuels our curiosity about the unknown and deepens our appreciation for the fragile, unique balance that makes Earth such a rare and habitable gem in the universe. But the planet does not only hold lessons about the forces that shape its own hostile environment, it also provides valuable clues about the formation and evolution of certain types of exoplanets known as hot Jupiters. Hot Jupiters are a class of gas giants that are unique in their sheer size and proximity to their parent stars. Unlike Jupiter in our own solar system, these massive planets orbit so close to their stars that their atmospheres are subjected to extreme heating and other intense forces. The study of HD 189733b, one of the most well-known examples of a hot Jupiter, has provided crucial insights into how these planets form and evolve. Researchers believe that hot Jupiters like HD 189733b do not originate near their stars. Instead, they are thought to form much farther away and then migrate inward due to gravitational interactions. As they get closer to their stars, their atmospheres experience rapid heating, which shapes their weather patterns and chemical compositions. By observing HD 189733b, scientists have gathered valuable evidence that supports the theory of planetary migration. The planet's rapid orbit, extreme atmospheric conditions, and unusual features, such as high-speed winds and chemical reactions unique to its environment, have given astronomers the opportunity to test their theories about how gas giants behave and evolve over time. The strange weather patterns on HD 189733b, including the formation of rain made from tiny glass-like particles, push the boundaries of our understanding. They challenge existing models of planetary atmospheres, forcing scientists to rethink how gases and elements behave in extreme conditions. These studies of exoplanets help refine our understanding of planetary systems, not just within our own solar system, but across the entire galaxy. HD 189733b's extreme environment provides a critical test case for theories about planetary weather, chemical interactions, and atmospheric evolution. This knowledge is not only essential for understanding other distant worlds, but can also provide important insights into how similar processes might unfold on planets closer to Earth. If humanity were ever to attempt the impossible task of building a base on HD 189733b, it would face a monumental challenge. The planet's weather, more ferocious than any storm on Earth, would make it one of the most inhospitable places imaginable. With winds exceeding 2,000 miles per hour and glass shards flying through the air, any structure built on this planet's surface would need to be made from materials capable of withstanding constant bombardment. The very idea of setting foot on this planet's surface would be a dangerous endeavor, let alone attempting to live there. The extreme heat is another nearly insurmountable obstacle. Temperatures on HD 18973b can reach up to 2,000 degrees Fahrenheit, hot enough to melt many metals, meaning that any human settlement would require highly advanced cooling systems and heat-resistant materials to survive. Additionally, the lack of a protective magnetic field exposes the planet to devastating radiation from its host star, meaning that any base would need thick shielding to protect inhabitants from harmful rays. The challenge of getting supplies and people to this distant world, located over 63 light-years away, would be another monumental hurdle. The immense distance means that sending even the most basic equipment would take years, if not decades. For a base to survive, it would need to be fully self-sustaining, capable of generating its own power, recycling water, and even producing food on site. All these obstacles paint a picture of a future far beyond our current technological capabilities. For now, HD 189733b remains one of the most extreme and uninhabitable worlds ever discovered, a reminder of how much we still have to learn about the universe and the forces that shape it. However, through continued study, scientists are gradually unlocking the mysteries of distant planets and the powerful forces that shape our universe. In the vast, seemingly infinite reaches of space, there exist planets so strange and extreme that they push the very boundaries of human imagination. One such planet is WASP-12b, an exoplanet unlike anything seen before, a world so close to its parent star that it is being torn apart. Scientists have been investigating this planet intensely, and what they have uncovered is nothing short of astonishing and terrifying. Located roughly 1 million miles from its star, WASP-12b is orbiting at a distance that is barely a fraction of the distance between Earth and the Sun. To put this into perspective, the Earth-Sun distance is about 93 million miles, so WASP-12b's proximity is roughly 1/8 that of our own planet. Due to this extreme closeness, the planet completes one full orbit in just 24 hours. An entire year on WASP-12b lasts only a single Earth day. This rapid orbit creates a planetary environment that is utterly alien. Unlike Earth, which takes 365 days to orbit the Sun, WASP-12b races through space in an eternal, never-ending cycle around its parent star. This proximity, however, comes at a tremendous cost. WASP-12b is subjected to such intense stellar radiation that it is constantly bombarded with heat and energy from its star, leading to devastating effects on its atmosphere, structure, and long-term viability. With temperatures soaring well beyond 2,000 degrees Fahrenheit, hotter than molten lava, WASP-12b's surface is a seething cauldron of chaos. At these temperatures, even metals would vaporize and any solid material would be reduced to gas. The planet exists in a state of constant turmoil where everything is in flux. The atmosphere of WASP-12b is unlike anything found on Earth. While our atmosphere is made up of relatively stable gases like oxygen and nitrogen, WASP-12b's atmosphere is volatile and ever-changing. The gases present are so exotic that they could not exist in cooler environments. In addition, the extreme temperatures on WASP-12b cause another bizarre phenomenon. The planet glows. Much like heated metal that radiates light, the surface of WASP-12b emits a faint, eerie glow as it radiates the intense heat it absorbs from its star. This makes the planet appear as though it is on fire, giving it a hellish, otherworldly appearance. Perhaps one of the most unusual features of WASP-12b is its shape. Unlike most planets, which are spherical, like WASP-12b is noticeably flattened at the poles and bulging at the equator. This distortion occurs because of the immense gravitational forces exerted by its star. Much like the moon's effect on Earth's tides, the gravity of the star pulls on the planet, stretching it out. The result is an oblate, egg-like shape that makes WASP-12b one of the most deformed planets ever observed. This gravitational stretch doesn't just alter the planet's shape, it also has a profound impact on its internal structure. The constant tug of gravity generates enormous friction inside the planet, adding even more heat to the already extreme temperatures. This additional heat causes the atmosphere to become even more unstable, creating a never-ending cycle of turbulence. But perhaps the most astonishing revelation about WASP-12b is the fact that it is slowly being destroyed. Scientists have found that the planet is losing its atmosphere at an alarming rate, roughly 100 million tons of gas every year. This is happening because the extreme heat from the star causes the atmosphere to expand, becoming less dense, while the powerful stellar winds push against the atmosphere, stripping away layers of gas. Over time, this process is leading to the planet's complete disintegration. In just a few million years, an incredibly short time on the cosmic scale, WASP-12b will be completely consumed by its star. As this destruction unfolds, WASP-12b leaves behind a trail of debris, creating a cloud of gas and material around its parent star. This offers scientists a rare opportunity to study the effects of extreme planetary disintegration. By observing this chaotic process, astronomers can better understand how planets evolve, die, and in some cases merge with their parent stars. Imagine standing on the surface of WASP-12b, although survival would be impossible. The sky would be unlike anything witnessed on Earth. The star would appear enormous, dominating the sky with an intensity so powerful that it would seem to blot out everything else. The light from the star could take on strange hues, from brilliant white and yellow to deep shades of orange and red, as the atmosphere scatters the light in ways that produce fiery, shifting colors. The air itself would be in constant motion, swirling with chaotic clouds of exotic gases, tinted with purple, blue, and red. Violent winds could sweep across the surface at thousands of miles per hour, stirring up towering plumes of gas. The sky might never truly grow dark, with the planet glowing faintly in a reddish or orange light due to the extreme heat radiating from its surface. Unlike Earth, where distant stars are visible in the night sky, the brightness of the star and the thick atmosphere would block out most of the cosmos, making it nearly impossible to see anything beyond the immediate surroundings. The story of WASP-12b is not just a tale of a planet in its final throes. It is a stark reminder of the forces at play in the universe. This planet gives scientists a rare opportunity to observe how extreme conditions of gravity, heat, and radiation shape a world. By studying WASP-12b, astronomers are gaining valuable insights into how planets evolve under extreme conditions, and the story raises profound questions about the fate of other planets. Could Earth-like planets orbiting their stars in similar proximity undergo similar transformations? Could our own planet experience such drastic changes billions of years in the future? By studying the life cycle of planets like WASP-12b, scientists are piecing together the puzzle of planetary evolution. In the process, we gain a deeper understanding of both our own past and what might lie ahead in the vast, uncharted future of the cosmos. WASP-12b is a prime example of a hot Jupiter, a gas giant similar in composition to Jupiter, but located much closer to its parent star. Its environment is so hostile that it challenges every known notion of what makes a planet habitable, with its surface temperatures reaching nearly 2,500 degrees Celsius, about 4,500 degrees Fahrenheit. This exoplanet is hotter than any natural process on Earth could ever generate. At these blistering temperatures, nothing remains solid or liquid. Everything on the surface is vaporized into gas, creating an environment completely devoid of land, oceans, or mountains. Instead, the entire planet's surface is a tempest of superheated gases swirling in chaotic storms. Moreover, the eerie glow of WASP-12b is the result of exotic gases like sodium and potassium, which, under the planet's extreme conditions, create a unique luminous effect. The planet's atmosphere reflects the star's light in a way that gives the illusion of a burning ember floating through space. But WASP-12b's fate is sealed. The immense gravitational forces from the star are not just stretching the planet's shape, they are also slowly stripping away its atmosphere. The extreme heat causes the atmosphere to expand and escape into space, with lighter elements like hydrogen and helium being lost first. Over time, even heavier gases may be torn away, hastening the planet's disintegration. This process of atmospheric escape, accelerated by powerful stellar winds, will eventually leave behind only the planet's dense core. In studying WASP-12b in real time, scientists are able to observe how extreme planets evolve and ultimately meet their demise. This offers a rare glimpse into the harsh and often destructive nature of cosmic forces. It also raises the question of what lies in store for other planets, like Earth, across the vast expanse of time. Will they too undergo such cataclysmic changes, or will they follow different paths toward their eventual end? Only time will tell, but for now, WASP-12b stands as one of the most extreme and fascinating examples of planetary destruction ever observed. The story of WASP-12b is a tale of dramatic change and cosmic turmoil, offering us a glimpse into the volatile, ever-evolving lives of planets caught in the fierce gravitational dance with their stars. Unlike Jupiter, which enjoys a relatively stable existence within our solar system, WASP-12b is a planet whose very atmosphere is being torn away at an astonishing rate. In this celestial battlefield, scientists have the opportunity to observe firsthand what might await other exoplanets in similarly extreme environments. This planet's conditions are extreme beyond imagination. Intense heat, combined with atmospheric escape and the continuous tidal stretching caused by its nearby star, makes WASP-12b one of the most unstable planets known to us. Its unstable nature has earned it a reputation as a natural laboratory, where scientists study how planets respond to the forces acting upon them, and how proximity to a star can reshape a planet's future. By observing WASP-12b's chaotic changes, researchers gain crucial insights into the fates of other exoplanets that may face similar conditions, providing us with a deeper understanding of how planetary systems evolve over the eons. WASP-12b's relationship with its star is an exemplary illustration of the immense power of celestial mechanics. The star's gravity doesn't just pull on the planet, it stretches it. This tidal stretching, like pulling on a rubber band, contributes significantly to the planet's atmospheric breakdown. As the planet is pulled and prodded by its star's powerful gravity, the atmosphere begins to lose its gases to space at a terrifying rate, accelerating the planet's transformation. The powerful radiation emitted by the star also plays a crucial role, ionizing the planet's atmosphere and propelling particles further and further away into the void of space. This dual effect of gravitational stretching and radiation causes WASP-12b to slowly lose material from both its surface and upper atmosphere, putting it on an irreversible path toward decay. For scientists, studying this exoplanet is more than just an exercise in observing a distant world. It's a key to unlocking the mysteries of the life cycle of planets, particularly hot Jupiters. These massive gas giants are not all that different from Jupiter itself, but their proximity to their stars makes them far more vulnerable. By watching WASP-12b, scientists hope to predict how other exoplanets may evolve, and when or if they might lose their atmospheres entirely, leaving behind nothing but barren, rocky cores. This understanding could one day inform predictions about planets far outside our solar system, potentially shedding light on the conditions required for a planet to maintain its atmosphere for billions of years. In fact, the study of WASP-12b also helps scientists investigate how planetary systems evolve over vast periods of time. As some exoplanets lose their atmospheres, they may eventually resemble Mercury or Earth's moon, dry, airless bodies stripped of any gaseous envelope that once surrounded them. These insights also serve as a reminder that even the most stable-looking planets can undergo radical transformations under the right conditions. If a spacecraft could somehow withstand the blistering heat and intense radiation of WASP-12b and return data to Earth, it would be providing us with an unprecedented look at a world unlike anything in our own solar system. The upper atmosphere of WASP-12b is an ever-changing cocktail of hydrogen, helium, sodium, and other volatile gases, constantly swirling in a superheated haze. The planet's surface is hardly even recognizable, if such a term can be used, because it is essentially an expanse of vaporized metals and other elements, continuously shifting and changing under the influence of temperatures that can melt or vaporize almost anything. As time goes on, WASP-12b's mass will continue to diminish. It may eventually shrink, becoming smaller and denser, or it could face an even more dramatic fate, eventually being completely consumed by its parent star, leaving behind only faint traces of its existence. This rapid process of loss, however, is what makes WASP-12b so interesting to scientists. It serves as a crucial case study for understanding how extreme heat and radiation can alter a planet's future, making it a powerful tool for learning about planetary destruction. Imagine, if you will, what it would be like for a spacecraft to enter the upper layers of WASP-12b's atmosphere. The conditions would change dramatically and unpredictably as the craft ascends, unlike the steady, stable atmosphere that surrounds Earth. The atmosphere of WASP-12b is in constant flux, with layers that shift in pressure and density under the relentless heat and radiation from the star. This dynamic environment creates unpredictable wind patterns that would pose significant challenges to any spacecraft trying to maintain a steady course. The spacecraft would need advanced technology capable of adjusting to these sudden shifts in real time, navigating the wild, turbulent conditions of an atmosphere that is anything but predictable. Beyond the turbulence, the spacecraft would also encounter fascinating chemical reactions occurring in the atmosphere, induced by the star's intense radiation. The radiation interacts with elements like sodium and potassium, which behave radically differently than they do on Earth. These elements absorb the light from the star and then re-emit it, creating glowing trails across the sky. It's almost as if the planet's atmosphere is alive, lighting up in a dazzling show of color. These reactions could produce stunning visual effects, turning the sky into an ever-shifting kaleidoscope of brilliant light and shadow. The extreme radiation doesn't just affect light, it also energizes the particles within the atmosphere, producing vibrant colors that would make the skies of WASP-12b seem completely alien compared to our own world. On top of this, the intense heat results in a truly bizarre phenomenon: clouds made entirely of vaporized metals. Under Earth's conditions, metals like iron and aluminum exist as solids or at most liquids. But on WASP-12b, the heat is so severe that even these dense substances exist as gases. This results in metallic clouds drifting across the planet's atmosphere, an awe-inspiring sight that is as dangerous as it is beautiful. Observing these processes is more than just an exercise in scientific curiosity. It could revolutionize our understanding of how atmospheres behave under extreme conditions. WASP-12b's atmosphere, with its constantly changing composition and violent reactions, provides a rare opportunity to study the behavior of materials and elements in a way they would be impossible to replicate here on Earth. The data gathered from this exoplanet could help scientists refine their models of how planetary atmospheres evolve, how they change over time, and what might cause them to break down. The future of WASP-12b, unfortunately, is not one of stability. Unlike Earth, which will experience gradual changes over the next several billion years, WASP-12b's fate is sealed by its proximity to its parent star. The relentless gravitational forces and radiation bombardment from the star are stripping the planet of its atmosphere and mass at an alarming rate. Eventually, WASP-12b may be reduced to little more than a lifeless, barren rock. Its rapid demise contrasts sharply with the more gradual evolution of planets in our own solar system, such as Earth, which will have billions of years to adapt to changes before the Sun reaches the red giant phase and possibly engulfs the inner planets. However, unlike the rapid destruction of WASP-12b, the outer planets in our solar system, including Jupiter and Saturn, may experience changes over a far longer period. As the Sun expands, these outer planets may undergo orbital shifts, but the process will unfold over billions of years, allowing ample time for adaptation. Earth and its neighbors may face their own destruction, but over a much slower and more gradual timeline. In contrast, WASP-12b provides us with a preview of a much more immediate and violent end. In studying WASP-12b, scientists gain a unique perspective on the different paths planets can take in their evolution. While planets like Earth may enjoy billions of years of stability before undergoing radical changes, others like WASP-12b are doomed to a far quicker and more destructive fate. This research underscores the fundamental connection between a planet's life cycle and its relationship with its star. Some planets are fortunate enough to experience stable, life-sustaining conditions, while others are subjected to the relentless forces of radiation and gravitational pull that speed up their destruction. In the vast expanse of space, many worlds are still waiting to be discovered, each with their own fate, and each with the potential to tell us more about the incredible diversity of planetary systems that exist beyond our own. The study of WASP-12b is just one chapter in the story of these distant worlds, but it offers an invaluable look at the destructive forces of the universe and the incredibly diverse paths that planets can follow. From this tiny, volatile planet comes a treasure trove of information that helps scientists understand not just the fate of planets, but the very nature of the cosmos itself. But if you were to turn your gaze further into the dark corners of space, you would encounter another mysterious world, one even darker than anything previously imagined. This planet, known as TAR-ES-2b, is the darkest planet ever discovered, absorbing nearly 97% of the light that reaches its surface. In a way, it is darker than even the deepest shadows found on Earth, more akin to the blackness of a black hole. This eerie absence of light raises profound questions about what causes such a planet to absorb so much radiation instead of reflecting it. And just as WASP-12b provides scientists with a window into the extreme behaviors of atmospheres, TAR-ES-2b offers a glimpse into a strange, unexplained corner of the universe where light seems to vanish entirely. In the vast expanse of the universe, the mysterious exoplanet known as TRES-2b stands out as an enigma, one that challenges the very limits of our understanding. While scientists continue to explore the intricate workings of planets beyond our solar system, TRES-2b presents an extraordinary case, sparking new questions about the nature of planetary atmospheres, light, and heat. This planet, which orbits a star far from our own, has one of the darkest surfaces ever discovered. But what exactly causes this extreme blackness, and how does it affect the planet's environment? The darkness of TRES-2b may not merely be the result of its position in space or the mere absence of light. It is likely caused by an unusual combination of chemical compounds in its atmosphere. Scientists have speculated that gases like carbon monoxide and carbon dioxide could be significant contributors to this profound lack of light. These compounds, rich in carbon, might be responsible for creating an extraordinarily dense and layered atmosphere. Such an atmosphere would trap light, preventing it from escaping and reinforcing the planet's eerie and ghostly appearance. But even more intriguing is the idea that there could be entirely unknown substances at play, substances that have yet to be identified by researchers. After all, the universe is filled with mysteries, and TRES-2b is a perfect example of how much there is still to learn about the cosmos. What makes TRES-2b even more fascinating is how drastically it differs from planets and moons in our own solar system. While certain worlds like Saturn's moon Titan also possess dark surfaces, none come close to the almost total lack of reflectivity exhibited by TRES-2b. Even the darkest planets in our solar system, such as the gas giants in the outer reaches, still reflect a faint amount of light, enough to give them some degree of glow. Not so with TRES 2b. This exoplanet absorbs nearly all the light that touches its surface, making it one of the darkest places we know. To put this into perspective, let's consider Earth. Our planet reflects about 30% of the sunlight that hits it, a factor that plays a key role in how we perceive the world. The oceans appear blue, the clouds are white, and the forests are green. Even our moon, which appears dark in some images, reflects around 12% of the sunlight that strikes it. TRES 2b, however, absorbs nearly all of the light reaching it, creating an entirely different and alien experience. This makes the planet an extraordinary subject of study, one that allows scientists to explore new avenues of research into extreme planetary environments. Yet, despite its profound darkness, TRES 2b is anything but cold. In fact, it is one of the hottest exoplanets ever discovered. With surface temperatures that soar to around 2,700 degrees Fahrenheit, 1,300 degrees Celsius, the heat on this planet is enough to melt most metals. This extreme temperature is primarily due to the planet's proximity to its parent star. TRES 2b is classified as a hot Jupiter, a type of gas giant that orbits extremely close to its sun. This proximity subjects the planet to intense stellar radiation, dramatically heating up its atmosphere. However, instead of reflecting some of this heat back into space, as planets with lighter surfaces tend to do, TRES 2b absorbs almost all of it. The result is a searing, blistering surface temperature, turning the planet into a glowing, burning black sphere. Some scientists suggest that the light-absorbing materials in the planet's atmosphere may even act like an exaggerated version of the greenhouse effect, trapping more heat than would normally be possible. This means that unlike Earth, where heat is distributed through atmospheric currents and oceanic exchanges, TRES 2b's atmosphere locks in the heat, creating a hostile and uninhabitable environment. On Earth, the interplay between light and shadow allows us to see the world around us. Our eyes rely on the contrast between illuminated surfaces and those in shadow to distinguish shapes and distances. On TRES 2b, however, this balance of light and dark is entirely absent. The planet's atmosphere, rich in metallic compounds and vaporized elements, absorbs nearly all the light that reaches it. This creates an environment of total darkness, no matter how close the planet is to its star. To imagine this scenario, think of walking through a thick fog on a moonless night. But instead of mist, you are surrounded by an almost inescapable and impenetrable darkness. Even the most powerful flashlights would struggle to cut through this blackness. The light they emit would be absorbed by the atmosphere before it could illuminate anything. On TRES 2b, the human eye would find it nearly impossible to adjust to such an environment. Where on Earth we rely on visible light to see, this planet demands an entirely different approach. In fact, any attempt to navigate the surface would require advanced imaging technologies, such as infrared or thermal cameras, to detect heat sources rather than relying on visible light. Without these tools, finding your way through the planetary landscape would be akin to walking through a pitch-black cave with no light source. But how then do scientists study such a distant and elusive world? The key lies in a technique known as transit photometry. This method involves closely monitoring the brightness of a star and looking for tiny temporary drops in that brightness. These dips occur when a planet passes in front of its star, partially blocking the starlight. By analyzing how much light is blocked during this transit, astronomers can gather critical data about the size of the planet and the amount of light it reflects. In the case of TRES 2b, scientists have found that its reflectivity, or albedo, is astonishingly low. In fact, it reflects less than 1% of the light that hits it. This is even darker than charcoal or the blackest synthetic paints ever created by humans. Essentially, TRES 2b behaves like a cosmic black hole, absorbing almost all the light that reaches it. Beyond this, scientists also employ a technique called spectroscopy, which involves studying how light interacts with the chemicals in a planet's atmosphere. When starlight passes through the gaseous envelope of a planet, certain wavelengths are absorbed by the atmospheric elements present. By analyzing this absorption, much like a prism creates a rainbow, astronomers can identify the specific gases and compounds in the planet's atmosphere. This method not only helps to illuminate the chemical composition of distant exoplanets like TRES 2b, but also plays a critical role in understanding the broader nature of planetary environments in the universe. In the grand scheme of astronomical research, TRES 2b is not just a planet of curiosity. It is a symbol of the vast and mysterious diversity of worlds that lie beyond our own solar system. While we are accustomed to the familiar, vibrant planets of our own neighborhood in space, TRES 2b shows us that the universe is full of surprises, with planets that can be dark, extreme, and utterly unlike anything we have known. As scientists continue to study planets like TRES 2b, they will gain insights into the chemical and physical processes that occur in extreme environments, potentially paving the way for discovering more Earth-like planets that could harbor life. But for now, TRES 2b remains an enigmatic world, a strange and inhospitable place, reminding us that there is still so much more to learn about the cosmos. Exoplanets are some of the most exciting and mysterious objects in the universe. Scientists use both ground-based and space telescopes to observe them, gathering data in different wavelengths of light. By tracking changes in brightness, astronomers can learn a great deal about a planet's properties, including its temperature, atmospheric composition, and the overall nature of its environment. These methods, when combined, allow scientists to piece together a much clearer picture of what distant planets are really like, despite the fact that they might be light years away. One such planet that has captivated the interest of astronomers is TARIS 2b. Though it lies far beyond our reach, the study of TARIS 2b provides invaluable insights into the processes that govern how planets form, evolve, and interact with their star systems. One of the most significant lessons that TARIS 2b has to offer is the role that a planet's proximity to its star plays in shaping its atmospheric conditions. Positioned extremely close to its parent star, TARIS 2b experiences intense and almost constant heating. This immense heat alters the planet's chemical makeup over time, causing a phenomenon known as atmospheric escape. During this process, lighter gases in the planet's atmosphere are continually stripped away and lost to the vastness of space. The longer this process continues, the more it can radically change the planet's environment, leaving behind only the heavier, more heat-resistant elements. This constant loss of lighter elements also has a profound impact on the planet's overall characteristics. For example, the presence of metallic elements in TRES 2b's atmosphere provides scientists with a unique opportunity to study how various materials interact with both heat and light. Understanding these interactions allows researchers to explore how a planet's atmospheric composition influences its appearance and, in turn, its climate. One of the defining features of TRES 2b is the fact that it is locked in an extremely close orbit around its host star. Unlike Earth, which takes 365 days to complete its orbit around the Sun, TRES 2b completes its orbit in less than 2 days, an incredibly short period of time. This close orbit means that TRES 2b is constantly struggling to withstand the immense heat and radiation emanating from its nearby star. Temperatures on the planet rise to around 500 degrees Celsius, which is high enough to vaporize many elements and compounds that would remain solid or liquid on Earth. This extreme heat results in an atmosphere filled with unusual metallic clouds that are excellent at absorbing light, which is a key reason why TARIS 2b appears so dark. Instead of reflecting sunlight as Earth does with its oceans and clouds, TARIS 2b absorbs nearly all the light that hits it. This makes it appear as a pitch-black void in the vastness of space, a stark contrast to most other planets. Most planets, including gas giants like Jupiter, reflect at least some portion of the light they receive from their stars. Even the darkest planets in our solar system, such as Mercury or Venus, reflect a fraction of sunlight. But TARIS 2b is different. It reflects less than 1% of the light that strikes its surface. To put this into perspective, even coal or black asphalt on Earth reflects more light than this mysterious world. Scientists have determined that the extreme darkness of TARIS 2b is likely due to its unique atmospheric composition. The planet's superheated environment allows certain light-absorbing substances, such as metallic vapors, possibly titanium oxide or sodium, to dominate the atmosphere. These substances function like a cosmic sponge, soaking up nearly all incoming light rather than reflecting it back into space. Moreover, TRES-2b is tidally locked, meaning that one side of the planet always faces its star while the other side remains in eternal darkness. This lack of planetary rotation results in the extreme and uneven distribution of heat. The side facing the star is continuously bombarded with energy, which makes it even more difficult for the planet to reflect light. If we could somehow travel to TRES-2b, we would be greeted by a world unlike any other, an alien environment where the weather is shaped by extreme heat, fierce storms, and potentially even metallic rain. Because TRES-2b is tidally locked, the dramatic temperature contrast between the day and night sides of the planet creates powerful wind currents. On the bright side of the planet, the superheated atmosphere rises and expands, while cooler air from the dark side rushes in to take its place. This constant flow of air could give rise to winds traveling at speeds of thousands of kilometers per hour, far stronger than any hurricane on Earth. Some scientists even speculate that molten metal droplets might condense in the upper atmosphere and fall as liquid iron rain. This rain, unlike the water-based precipitation we experience on Earth, would quickly evaporate as it nears the scorching lower atmosphere. On the night side of the planet, there is no direct sunlight, meaning temperatures could plummet dramatically compared to the day side. This extreme temperature difference could lead to unpredictable and volatile weather patterns, as well as even more extreme atmospheric conditions. TRES-2b is a world of extremes, where swirling clouds of metallic gas could fill the sky, and storms made of molten iron might rage for days or weeks at a time. One of the greatest mysteries in the field of astronomy is whether life could exist beyond Earth. Given the harsh and extreme environment of TRES-2b, one might assume that life would be impossible there. After all, life as we know it requires energy, stability, and protection from harmful radiation, resources that seem absent on this dark and hostile planet. Perhaps the biggest barrier to life on TRES-2b is its ability to absorb almost all the light that reaches it, meaning there would be virtually no visible sunlight to support processes like photosynthesis, which is the method by which plants and other organisms convert light into energy. Without sunlight, any potential life forms would have to rely on alternative sources of energy, such as the heat radiating from the planet's interior, or perhaps chemical reactions occurring in the atmosphere. On Earth, scientists have discovered extremophiles, microorganisms that thrive in some of the most extreme environments on the planet, like deep-sea hydrothermal vents where temperatures can exceed hundreds of degrees Celsius. If life exists on TRES-2b, it would likely be even more resilient than these Earth-based extremophiles, adapting to survive in complete darkness, enduring searing temperatures, and withstanding exposure to potentially toxic atmospheric chemicals. That said, TRES-2b is a gas giant, which means it likely lacks a solid surface. If life were to exist, it would have to float within the dense, swirling atmosphere, much like some microscopic organisms that live in Earth's clouds. Life on TRES-2b, if it exists at all, would be unlike anything we've encountered before, perhaps offering an entirely new chapter in the search for life beyond our planet. However, given the extreme heat and the absence of a stable environment for ecosystems to take root, the likelihood of life thriving on the planet TRES-2b remains remarkably slim. Studying this enigmatic world, however, is no simple task. TRES-2b's surface absorbs almost all the light that reaches it, making it one of the darkest planets known to us. Traditional telescopes cannot offer a clear view, forcing scientists to rely on more indirect and innovative methods to gather data. Rather than directly observing the planet, astronomers must look at how TRES-2b's gravity impacts its star or measure the heat it emits through infrared wavelengths. One of the most challenging aspects of studying this planet is its profound darkness. Telescopes and spacecraft typically rely on light to collect information, but TRES-2b reflects nearly none of it, creating an almost impenetrable veil for traditional imaging techniques. To overcome this hurdle, researchers have turned to infrared sensors, which are capable of detecting the faint heat emissions from the planet. These infrared readings are instrumental in revealing some of the planet's hidden characteristics, including details about its temperature and atmospheric composition. The challenges don't end there. Communicating with spacecraft that would venture to TRES 2b presents another monumental issue. Since the planet orbits a distant star far beyond our solar system, the signals would take a prohibitively long time to travel between Earth and the spacecraft. As a result, any future missions to this dark world would need to rely on advanced technologies that could withstand these harsh conditions and still send and receive data efficiently. Despite the immense challenges, astronomers persist in their efforts to study TRES 2b. Tools like NASA's James Webb Space Telescope have enabled researchers to continue gathering vital information, particularly by analyzing the way light interacts with the planet's thick atmosphere. Through this, scientists hope to unlock more secrets of this dark, mysterious world, secrets that could change our understanding of how planets form and evolve under different cosmic conditions. TRES 2b is undoubtedly one of the most bizarre and captivating planets discovered thus far. Its oppressive darkness, blistering heat, and volatile weather patterns make it a far cry from any planet within our own solar system. Yet, despite its hostile conditions, studying TRES 2b offers valuable insights into the broader processes that govern the formation of planets in other regions of the universe. For instance, if a planet is enveloped by a thick atmosphere or surrounded by floating space debris, these factors would present additional obstacles to communication. Such barriers would make sending and receiving signals even more difficult, forcing scientists to think creatively and develop novel methods for maintaining communication with spacecraft, exploring these distant worlds. Exploring TRES 2b's surface would present further complications. Rovers and landers would need to be specially designed to endure its rough and uneven terrain. Given that much of the planet is shrouded in perpetual darkness, these machines would require not only durability, but also advanced navigation systems capable of safely guiding them through the challenging conditions. Gathering samples or conducting surface analysis would be no easy task either. Instruments would need to be capable of functioning in an environment where light is virtually non-existent. This might involve relying on autonomous systems, machines that could operate independently without needing constant communication with Earth to ensure everything was functioning properly. The environmental factors on TRES 2b could be equally unforgiving. Extreme temperatures, unpredictable weather, and the potential presence of toxic gases all add to the challenge. In order to ensure the survival of any spacecraft exploring the planet, scientists would need to design robust protective shields and materials capable of withstanding these hostile conditions. For instance, these systems might have to endure freezing cold temperatures, crushing atmospheric pressure, or even harmful chemical environments. All of these considerations highlight the level of sophistication and precision required in the technology that would be needed to explore such a world. The complexities involved in exploring a planet that exists in near-perpetual darkness require a blend of ingenuity, groundbreaking engineering, and an in-depth understanding of the unknown. As we continue to probe the mysteries of our universe, the study of planets like TRES 2b reminds us of the vastness of the unknown and the extraordinary challenges that await those who seek to explore it. One of the most fascinating aspects of the universe, and one that pushes the limits of our understanding, is the concept of strange matter. While we are familiar with ordinary matter, the stuff that makes up everything we see and touch, there are other, far stranger forms of matter in existence. One such form, known as strange matter or strange quark matter, is hypothesized to exist under conditions of extreme pressure and density. These conditions are so extreme that they can only be found in the cores of neutron stars or in theoretical objects known as strange stars. Strange matter has intrigued scientists because it challenges everything we know about the fundamental building blocks of matter. Theoretically, strange matter could also exist as tiny droplets known as strangelets, which could potentially exist in space or even on Earth. But before we delve into this strange substance, it's important to first understand the different types of matter that make up our universe, starting with the most familiar. Ordinary matter, also called atomic matter, is the kind we interact with every day. It's made up of atoms, which are the building blocks of everything from the smallest particles to the largest galaxies. Even though atoms form the foundation of matter, they are mostly empty space. Almost all of an atom's mass is concentrated in its nucleus, which consists of protons, positively charged particles, and neutrons, particles with no charge. These protons and neutrons, in turn, are composed of even smaller particles called quarks. Quarks come in different varieties, with the most common being the up quark and the down quark. A proton consists of 2 up quarks and 1 down quark, while a neutron contains 2 down quarks and 1 up quark. The way these quarks interact within atomic nuclei is what determines the structure of matter itself. When protons and neutrons come together in large numbers, they form nuclear matter, the substance that makes up the core of atoms. This nuclear matter exists in a dense, liquid-like state, where the protons and neutrons can move freely but remain bound together by powerful forces. However, when subjected to extreme pressure, such as in the core of a neutron star, something extraordinary occurs. Nuclear matter becomes so tightly compressed that protons and neutrons break apart, releasing their quarks. This leads to the creation of quark matter, a superdense state of matter composed entirely of free quarks. There are 2 types of quark matter: non-strange quark matter, made up of only up and down quarks, and strange quark matter, which contains up, down, and the additional strange quarks. Strange matter, then, is a specialized form of quark matter, characterized by the presence of strange quarks. While up and down quarks are abundant throughout the universe, strange quarks are much rarer and only form under extreme conditions. Scientists believe that when nuclear matter is compressed beyond a critical density, such as in the heart of neutron stars, the protons and neutrons dissolve into their constituent quarks, forming quark matter. Under the right conditions, this quark matter can transition into strange matter. What makes strange matter especially intriguing is the possibility that it may be the most stable form of matter in the universe. If this hypothesis holds true, it could mean that strange matter is more stable than even atomic or nuclear matter. If strange matter can exist indefinitely, it would fundamentally alter our understanding of the universe. One of the most captivating aspects of this theory is the strange matter hypothesis, or the Bodmer-Witten conjecture, which proposes that strange matter could be the true, fundamental state of matter. According to this idea, all of the matter we see around us, planets, stars, and even our own bodies, could be in a temporary, less stable state. Over time, or under the right conditions, atomic nuclei could potentially transform into strange matter, a process that might begin with the creation of strangelets. These tiny droplets of strange matter could, in theory, trigger a chain reaction, slowly converting everything they touch into strange matter. Fortunately, there is no strong evidence suggesting that such a transformation is happening naturally anywhere in the universe, so there's no immediate danger of the universe turning into strange matter. Nonetheless, the possibility that strange matter could exist and play a role in the universe's future remains one of the most fascinating and mysterious ideas in modern physics. However, some scientists believe that small amounts of strange matter might already exist in the universe, possibly formed during some of the most powerful and violent cosmic events known to humankind, such as neutron star collisions. Neutron stars are the remnants of massive stars that have exploded in supernovae. These remnants are incredibly dense, so dense that a single teaspoon of neutron star material would weigh billions of tons. Within these stars, some scientists propose the pressure could be high enough to generate strange matter, a bizarre and exotic form of matter that behaves in ways unlike anything seen in the ordinary world. In theory, the heart of neutron stars, where gravity is overwhelmingly intense, could create the conditions needed for this strange substance to form. If enough strange matter accumulates within a neutron star, the entire star might undergo a dramatic transformation into what could be called a strange star. The possibility that strange matter could exist elsewhere in space is also intriguing. Tiny fragments of this material, known as strangelets, might drift through space, ejected during extreme cosmic events, and could potentially be detected by the tools of modern physics. These strangelets could make their way to Earth, where they might be picked up either by cosmic rays or by experiments designed to probe exotic particles. One of the most advanced places where scientists are testing the limits of fundamental physics is at the Large Hadron Collider, LHC, where high-energy particle collisions recreate some of the most extreme conditions in the universe. Some theories even suggest that strange matter could be produced in these high-speed collisions, though it would likely decay very quickly, making detection difficult. The possibility that strange matter exists and is stable enough to persist longer than anticipated could revolutionize our understanding of physics. In such a scenario, the universe might naturally prefer to exist in a strange matter state, rather than in the atomic state we observe today. This mind-bending idea suggests that ordinary matter, atoms, protons, neutrons, could be just one phase in a much grander and stranger picture of the cosmos. If a strangelet were to collide with a neutron star, it could set off a chain reaction, triggering a complete transformation of the neutron star into a strange star. Such an event would be a dramatic and potentially catastrophic change in the star's structure and could radically alter the surrounding space. Should strange matter be more stable than ordinary matter, some speculate that it might even be harnessed for futuristic applications, though this remains purely theoretical for the time being. In addition, some scientists have speculated that objects like quark stars or strange stars may already exist in the universe, but these stars would be extraordinarily difficult to detect with current technology. From a distance, they might appear to be nothing more than neutron stars. To truly understand whether strange matter is out there, scientists must first delve deeper into the nature of matter itself. At its core, strange matter is a state of matter composed of quarks, the fundamental building blocks that make up protons and neutrons. Under normal conditions, quarks combine in specific ways to form protons and neutrons, the particles that make up the atomic nucleus. However, under immense pressure, the forces holding these ordinary particles together can no longer resist the crushing density, and new forms of quark matter can begin to form. This transformation happens when particles like neutrons are squeezed under conditions that push them beyond their normal limits. The result is the formation of quark matter, an exotic state of matter that could give rise to strange matter under certain conditions. To understand how strange matter forms, we need to explore the concept of degeneracy pressure, a force that prevents extremely dense objects like white dwarfs and neutron stars from collapsing under their own weight. Imagine a subway car at rush hour. The more people squeeze into the car, the more cramped everyone becomes. Similarly, when particles are forced into extremely dense spaces, they are forced into higher energy states due to the Pauli exclusion principle. This principle states that no two identical particles can occupy the same quantum state at the same time. As a result, when matter is squeezed under extraordinary pressure, the particles resist the collapse by occupying higher energy states, a phenomenon known as degeneracy pressure. But there comes a point when the pressure becomes so extreme that it overpowers even this resistance, and the normal rules of matter begin to break down. When this happens, quarks inside neutrons may begin to transform into a new type of quark, known as the strange quark. This transformation leads to the creation of strange matter, a form of matter that may be more stable than the neutron star material we typically observe. In a neutron star, neutrons are made up of 2 down quarks and 1 up quark. Down quarks are negatively charged, while up quarks have a positive charge. In the normal matter we encounter on Earth, down quarks outnumber up quarks, contributing to the degeneracy pressure that keeps the star from collapsing. But under extreme conditions, some of these down quarks may change into strange quarks. Although strange quarks are slightly heavier than down quarks, this transformation lowers the overall energy of the system, making it more stable and creating what scientists call strange matter. If the conditions inside a neutron star become dense enough to form quark matter at its core, the star is sometimes referred to as a hybrid star. While scientists suspect that hybrid stars may exist, proving this hypothesis is incredibly challenging. For one thing, no one knows exactly how much pressure is needed to trigger the transition from neutron matter to quark matter. Estimates suggest that this transformation may occur when the density inside a neutron star reaches about 100 times that of an atomic nucleus. To put that in perspective, a sugar cube-sized piece of neutron star material would weigh billions of tons. Even more daunting is the fact that physicists are still working to understand the behavior of quarks under these extreme pressures. The strong nuclear force that governs quarks is highly complex, and current mathematical tools struggle to accurately model quark behavior in such extreme conditions. One promising method, known as lattice quantum chromodynamics, QCD, could offer insights, but it is hindered by the fermion sign problem, a difficult obstacle that makes these calculations incredibly challenging. So if strange matter exists, where might we find it? The most promising place to discover strange matter could be during the violent mergers of neutron stars. When two neutron stars collide, the impact is so powerful that it sends shock waves across the universe, creating gravitational waves and high-energy light. During these cataclysmic events, some of the strange matter at the core of the stars could be ejected into space. If astronomers are able to detect this material before it decays, it could provide definitive evidence for the existence of strange matter, offering a glimpse into one of the most exotic and mysterious states of matter in the universe. However, there are two major challenges in the pursuit of understanding strange matter, both of which limit our ability to study this strange phenomenon. First, the decay rate of strange matter remains an enigma. Scientists currently do not know how quickly it breaks down once it escapes the dense confines of a neutron star. If it decays too rapidly, it may never reach our telescopes, preventing us from detecting it. Second, neutron star mergers, the rare cosmic events where two neutron stars collide, are not only infrequent, but they also occur in distant regions of space. Only a handful of neutron star pairs lie close enough to Earth to study them in detail. This scarcity makes it even more difficult to find and study strange matter. One of the most captivating possibilities in modern physics revolves around the strange matter hypothesis. This intriguing theory proposes that nuclear matter, the building blocks of protons and neutrons, is not the most stable form of matter. Instead, it could be metastable, meaning it could theoretically decay into a more stable form called strange matter over an incredibly long period. If this hypothesis is correct, it would open the door to a radically new understanding of the universe, suggesting that strange matter exists in several distinct forms across the cosmos. These forms could include quark stars, strange stars, and even strangelets. Quark stars are one such possible manifestation of strange matter. Unlike hybrid stars, which only have a quark core, quark stars are entirely composed of strange matter, stretching from their cores to their surfaces. These bizarre objects would be only a few kilometers wide, remarkably small on cosmic scales, yet they would contain a mass greater than our sun's. A quark star might even possess a thin outer crust made of ordinary nuclear matter, adding to its complexity. Although no quark stars have yet been observed, their theoretical existence sparks intense interest among astrophysicists. Then there are strangelets. These are minute pieces of strange matter, potentially as small as atomic nuclei. Scientists theorize that strangelets could be formed in a variety of ways, such as during the formation of strange stars, when these stars collide, or even when a nucleus undergoes an unusual type of decay. If strangelets do exist, they could theoretically travel through space, perhaps even reaching Earth. However, despite years of searching, no direct evidence of strangelets or quark stars has yet been found. Nevertheless, researchers continue to search the skies for clues that might confirm the existence of strange matter. Should this hypothesis be proven true, it could dramatically shift our understanding of the universe and the fundamental nature of matter itself. Another fascinating aspect of the universe that both mystifies and intrigues scientists is radiation, a form of energy that travels through space, either as waves or moving particles. Radiation exists in two main types: ionizing radiation and non-ionizing radiation. The primary difference between these two forms lies in the amount of energy they carry and their ability to interact with atoms and molecules. Ionizing radiation is the more powerful of the two. It possesses enough energy, greater than 10 electron volts, to knock electrons out of atoms, a process called ionization. When atoms lose electrons, they become electrically charged, turning into ions. This process can break chemical bonds and cause damage to biological systems, making ionizing radiation potentially harmful to living organisms. Common sources of ionizing radiation include radioactive materials. These materials emit various types of radiation: alpha radiation, beta radiation, and gamma radiation. Alpha radiation consists of helium nuclei made up of 2 protons and 2 neutrons. Beta radiation consists of high-speed electrons or positrons. Gamma radiation, on the other hand, is a form of high-energy light or photons. X-rays, which are commonly used in medical imaging, also fall under the category of ionizing radiation. Even cosmic rays, high-energy particles from space, interact with Earth's atmosphere to produce secondary radiation, including muons, mesons, neutrons, and positrons. Within the electromagnetic spectrum, gamma rays, X-rays, and the high-energy portion of ultraviolet light are considered ionizing radiation. These waves have sufficient energy to strip electrons from atoms, potentially causing lasting damage. On the other hand, ultraviolet radiation, though not strong enough to ionize atoms, can still damage molecules, leading to effects like sunburns. This highlights a crucial distinction. While ionizing radiation can alter atomic structures directly, non-ionizing radiation primarily causes atomic bonds to vibrate, generating heat. This is how microwave ovens work. They use non-ionizing radiation to heat food. Infrared radiation, which makes Earth warm, also falls under the category of non-ionizing radiation. While non-ionizing radiation is generally considered safer than its ionizing counterpart, prolonged exposure can still lead to harm. For example, excessive ultraviolet light can cause skin damage, raising the risk of skin cancer. This serves as a reminder that even seemingly harmless forms of radiation can be dangerous if exposure is prolonged. The term radiation comes from the way energy spreads outward from its source in all directions, similar to ripples on the surface of a pond. This spreading behavior follows a predictable pattern, governed by a fundamental rule in physics known as the inverse square law. According to this principle, the intensity of radiation decreases as you move further from its source. For example, doubling the distance from a radiation source reduces the intensity by a factor of 4. This is why standing farther away from a radioactive object reduces exposure and the associated risks. When ionizing radiation strikes living cells, it can inflict damage on important molecules, including DNA. Since DNA contains the blueprints for cellular function and reproduction, damage to it can lead to cell death. In severe cases, cells may no longer be able to repair themselves and die. If the damage causes changes in the DNA, mutations can occur, potentially leading to uncontrolled cell growth and cancer. The likelihood of developing cancer due to ionizing radiation depends on several factors: the dose of radiation absorbed, the type of radiation, and the sensitivity of the affected tissue. Some tissues and organs are more vulnerable to radiation than others, and repeated or high-dose exposure increases the risk of long-term damage. In addition to electromagnetic waves, radiation can also come in the form of subatomic particles. These include alpha particles, beta particles, neutrons, and protons, each with unique characteristics. Alpha particles are large and slow-moving, and they can be blocked by something as simple as a sheet of paper. Beta particles are smaller and faster, capable of penetrating materials like plastic or thin metal. Neutrons, unlike other types of radiation, are electrically neutral, allowing them to penetrate deeply into materials. Proton radiation, which consists of high-energy protons, is also capable of causing ionization. Although most of these particles do not travel far through matter, neutrons can penetrate deep into materials, posing a particular challenge in certain contexts. Radiation is naturally present in our environment. Some of it comes from space in the form of cosmic rays, while other sources include the Earth's soil and rocks, which contain small amounts of radioactive materials. Ionizing radiation is invisible to the human eye, so special instruments, such as Geiger counters, are used to measure radiation levels. In some cases, radiation can cause materials to emit light, such as Cherenkov radiation, the blue glow seen in nuclear reactors. Radioluminescence, the phenomenon behind glow-in-the-dark materials, also occurs as a result of radiation. While radiation can be dangerous, it also has many beneficial uses in fields such as medicine, research, and industry. X-rays, for instance, play a crucial role in diagnosing diseases, while radiation therapy is used to treat cancer. Despite the risks, radiation is an indispensable tool that continues to revolutionize our understanding of the natural world. Radiation, while a natural part of the universe, can be both benign and perilous. It surrounds us in various forms, some of which have little to no effect on our health, while others can pose substantial risks, especially when exposure is excessive or prolonged. The fundamental challenge lies in the fact that radiation can cause damage to biological tissues, leading to a range of harmful effects, from cellular mutations to more severe consequences like cancer. At the most basic level, radiation consists of high-energy particles or waves that have enough energy to remove tightly bound electrons from atoms, a process known as ionization. It is this ionization capability that makes radiation potentially hazardous, as it can disrupt the delicate balance of biological systems. This interaction can cause a variety of physical effects, depending on the type of radiation and the amount of exposure. Exposure to high doses of radiation can be acutely harmful. Short-term exposure to intense radiation, especially in the form of ionizing radiation, can result in acute radiation syndrome, ARS. ARS manifests in several ways, including skin burns, hair loss, damage to internal organs, and in extreme cases, death. The severity of these effects often depends on the level and duration of exposure. Even in cases of lower doses, the risk to health is still significant, particularly when exposure happens over long periods. Chronic exposure increases the likelihood of developing cancers, notably thyroid cancer, when radioactive iodine is involved. The precise risk associated with cancer from radiation exposure is still not fully understood. However, the data gleaned from survivors of catastrophic nuclear events, such as the bombings of Hiroshima and Nagasaki or the Chernobyl disaster, has been instrumental in shaping current scientific understanding. These survivors provide some of the most valuable data, offering insights into the long-term health effects of radiation exposure. Yet, the International Commission on Radiological Protection, ICRP, acknowledges that risk calculations are fraught with uncertainty. They caution that while population-based studies can provide valuable general estimates, they might not offer the precision needed for individual risk assessments. Interestingly, the Earth's atmosphere plays a crucial role in shielding us from certain types of radiation, particularly ultraviolet UV radiation. The ozone layer, located high above the Earth's surface, acts as a protective barrier against harmful UV rays. Without this layer, the planet would be exposed to far greater levels of radiation, leading to severe biological consequences. For instance, ultraviolet light, though not strong enough to ionize atoms, still carries enough energy to cause damage to DNA, particularly through the formation of pyrimidine dimers. These mutations can interfere with normal cellular function and lead to the development of cancer over time. The ozone layer absorbs about 98% of the most harmful ultraviolet radiation, specifically UVB and UVC rays, preventing them from reaching the Earth's surface. UVB rays, for example, are directly linked to sunburns and an increased risk of skin cancer. Although some UV radiation does manage to reach the Earth's surface, the ozone layer's protective properties help mitigate these risks, particularly for living organisms. Interestingly, scientists refer to certain highly energetic ultraviolet light found in space as vacuum ultraviolet, a form of radiation with negligible biological impact, as it never reaches Earth's surface. However, not all radiation is naturally occurring. Human-made sources, like X-ray machines, also emit radiation. X-rays are a type of electromagnetic radiation with a very short wavelength, less than 1/1,000,000th of a meter. These waves carry immense energy, enough to interact with atoms in such a way that electrons are either moved to higher energy levels or completely removed, a process known as ionization. When X-rays pass through the human body, different tissues absorb them at different rates. Dense tissues, like bones, absorb more X-ray energy than softer tissues, which is why bones appear white on X-ray images, while softer tissues appear darker. This contrast allows doctors to use X-rays to detect fractures, tumors, and other medical conditions. Though the sun does produce X-rays, the Earth's atmosphere absorbs them before they can reach the surface, which is fortunate since prolonged exposure to X-rays can be harmful. Gamma rays, even more energetic than X-rays, present an even greater danger. These rays have wavelengths smaller than 31 trillionths of a meter, and their frequencies exceed 10 quintillion cycles per second. Gamma rays are produced in nuclear reactions, often from unstable atomic nuclei shedding excess energy. Unlike other forms of radiation that consist of particles, gamma rays are purely energetic waves. This makes them incredibly difficult to block, as they can penetrate deeply into materials. While the Earth's atmosphere protects us from most gamma radiation from outer space, it is not foolproof. Gamma rays remain a significant hazard in specific contexts, such as during nuclear accidents or as part of certain cancer treatments, like radiation therapy. The difficulty in shielding against gamma rays stems from their deep, penetrating ability, which requires dense materials like lead or uranium to block. In the event of a nuclear disaster, gamma radiation can spread far and wide, posing serious health risks to anyone in its path. In contrast to gamma rays, alpha particles are much larger and heavier. Composed of 2 protons and 2 neutrons, essentially forming the nucleus of a helium atom, alpha particles carry a strong positive charge. This makes them interact intensely with matter, but they can only travel short distances, just a few centimeters in air, before they lose all their energy. Thankfully, alpha particles can be stopped by something as simple as a sheet of paper or even the outer layer of skin. However, if substances that emit alpha particles, such as radium or polonium, are inhaled or ingested, they become highly dangerous. Once inside the body, alpha particles can damage tissues and DNA, leading to a significantly higher risk of cancer. In fact, alpha radiation is at least 20 times more damaging per unit of energy than X-rays or gamma rays when it comes into direct contact with living tissue. In space, a small percentage of cosmic rays consists of high-energy alpha particles, which can penetrate the human body and even thin metal shields. This is one of the reasons astronauts are at heightened risk of exposure to this type of radiation. Fortunately, on Earth, we are largely protected by our magnetic field and thick atmosphere, which act as shields against these cosmic rays. Beta radiation, on the other hand, involves fast-moving particles, either electrons or positrons. While not as dangerous as gamma rays, beta particles are more penetrating than alpha particles. Beta radiation can be divided into 2 types: beta minus radiation, which occurs when a neutron in an atom decays into a proton and emitting an electron and an antineutrino, and beta plus radiation, which involves the emission of a positron, the antimatter counterpart to the electron. When a positron encounters an electron, the 2 particles annihilate each other, releasing gamma photons. Beta radiation requires denser materials for shielding compared to alpha radiation, though it can be stopped by a few millimeters of metal or several centimeters of plastic. Interestingly, beta radiation is sometimes used in medical treatments, particularly for certain types of cancer. It can be employed in radiotherapy to target superficial tumors, where it can destroy cancerous cells by damaging their DNA. Neutron radiation is a rarer form of radiation that does not consist of charged particles or electromagnetic waves, but rather free neutrons, neutral subatomic particles. Neutron radiation is mostly produced during nuclear fission or fusion reactions, such as those occurring in a nuclear reactor or during a nuclear explosion. Neutron radiation is particularly dangerous because neutrons can penetrate deep into materials, often more effectively than even gamma rays. This deep penetration makes neutron radiation extremely difficult to shield against, requiring specialized materials like concrete, water, or boron-containing compounds to absorb and neutralize it. A fascinating aspect of neutron radiation is its ability to induce a process known as neutron activation. This occurs when neutrons interact with certain materials, transforming them into radioactive substances. Neutron activation is crucial in the creation of radioactive materials, which are used in various fields, including medicine, research, and industry. Even slow-moving neutrons, known as thermal neutrons, can cause this activation, making them incredibly effective at turning ordinary materials into radioactive ones. Unlike other types of radiation, neutrons do not cause ionization directly by interacting with the electrons of an atom. Instead, because they are electrically neutral, they interact differently with matter. Nonetheless, the deep penetration and activation potential of neutrons make them one of the most potent forms of radiation, particularly in high-energy environments like nuclear reactors. As we can see, radiation in all its forms is a complex and multifaceted phenomenon. While much of the radiation we encounter on a daily basis poses little to no harm, certain types, especially ionizing radiation, can be highly dangerous, particularly when exposure is uncontrolled or excessive. Understanding the different types of radiation and their effects on living organisms is crucial, not only for ensuring the safety of those working with radiation in various industries, but also for protecting public health in an increasingly radiation-saturated world. Neutrons, despite being neutral in charge, can play a pivotal role in altering the very fabric of matter. When these subatomic particles interact with atomic nuclei, they can cause instability within the nucleus. This destabilization sets the stage for the release of radiation in the form of energy or particles, which is why neutrons are often described as indirectly ionizing. Unlike other forms of radiation, neutrons don't ionize atoms in the traditional sense, but they still induce radiation by triggering processes that lead to ionization. Even neutrons with minimal kinetic energy, seemingly harmless in their motion, retain the potential to cause significant ionization. Thus, they present a considerable radiation hazard, especially when their effects accumulate over time. However, not all materials are equally susceptible to neutron-induced activation. Water, for instance, which makes up a significant portion of the Earth's surface and our bodies, is relatively resistant to neutron activation. The two main elements in water, hydrogen and oxygen, can capture neutrons and become isotopes of slightly heavier versions of themselves. But in this case, the transformation doesn't lead to meaningful radioactivity. Hydrogen, in particular, requires a rare multiple of neutron absorptions to activate, while oxygen would need to absorb 2 additional neutrons. As a result, water remains only faintly radioactive under neutron exposure, posing minimal risk to living organisms or the environment. In contrast, some materials are highly prone to neutron activation. Sodium, which is abundant in salt, particularly sea salt, is one such material. Sodium only requires a single neutron to be absorbed to become sodium-24, a highly radioactive isotope. This isotope is not stable and undergoes beta decay, a process in which it emits beta particles, electrons, as it breaks down into other elements. With a half-life of only about 15 hours, half of the sodium-24 atoms will decay into a different form of matter within that time, emitting radiation in the process. The presence of neutrons in the environment, therefore, can directly influence the radioactivity of certain substances, creating risks that may not be immediately apparent. Neutrons with high velocities, commonly referred to as high-energy neutrons, are especially potent. These energetic neutrons, unlike their slower counterparts known as thermal neutrons, possess the ability to ionize atoms directly. One of the ways they achieve this is by colliding with atomic nuclei at high velocities, transferring enough kinetic energy to knock atoms out of molecules, thereby breaking chemical bonds. This leads to the ejection of electrons from atoms, a hallmark of ionization. The resulting chemical-free radicals, highly reactive molecules, can cause serious damage to biological tissues. This form of damage is particularly concerning when dealing with high-energy neutrons, as the ejected protons, which are positively charged, can go on to ionize additional atoms. Another mechanism by which high-energy neutrons cause ionization is through a process known as neutron spallation or knockout reactions. When a high-energy neutron collides with a hydrogen nucleus, it can cause the nucleus to expel a proton, much like how a billiard ball transfers energy upon striking another ball. These ejected protons are capable of ionizing other atoms, compounding the potential for damage. What makes high-energy neutrons particularly dangerous is their ability to travel vast distances in open air. These neutrons can travel hundreds or even thousands of meters before losing their energy, which allows them to penetrate solid materials several meters deep. This characteristic is why thick shielding, often made of hydrogen-rich substances like water or concrete, is essential to block their effects, especially in environments like nuclear reactors. Nuclear reactors are among the most common places where neutron radiation is a significant concern. However, neutron radiation is not limited to artificial sources. Natural high-energy particles constantly bombard the Earth from the vast expanse of space. These cosmic particles originate from 2 primary sources, the Sun and deep space. Our sun emits a continuous stream of charged particles, mainly protons, in what is known as the solar wind. Occasionally, the sun releases intense bursts of particles during phenomena like coronal mass ejections, CMEs, which can greatly increase the flow of high-energy particles toward Earth. Beyond our solar system, the most energetic particles that reach Earth are galactic cosmic rays. These rays are less frequent than solar particles, but are much more powerful. These cosmic rays primarily consist of protons, with some made up of alpha particles, helium nuclei, and even heavier atomic nuclei. Scientists believe these cosmic rays are generated by some of the universe's most violent events, such as supernova, exploding stars, and gamma-ray bursts, GRBs, which involve intense magnetic fields capable of accelerating particles to extraordinary speeds. Additionally, some theories propose that these cosmic rays might originate from quasars, which are powerful energy jets thought to have existed in the early universe. Not all radiation, however, has the ability to ionize atoms. Some forms of radiation do not carry enough energy to knock electrons off atoms and are classified as non-ionizing radiation. This category includes radio waves, microwaves, infrared light, and certain types of ultraviolet UV light. Though non-ionizing radiation does not create charged ions, it can still interact with matter in other ways. For instance, it can alter the vibrational or rotational energy levels of molecules, which can lead to changes in their properties. While scientists are still exploring the full range of biological effects of non-ionizing radiation, it is clear that different types of radiation can have varied impacts on living organisms. Interestingly, even non-ionizing radiation can cause ionization under extreme conditions. If a material absorbs enough heat, its atoms can become excited to the point where they ionize. This phenomenon explains why fire can produce ionization and why food browns when cooked under intense heat, such as when using infrared radiation in broiling. It is fascinating how this seemingly innocuous form of radiation can, under the right conditions, trigger ionization, blurring the line between ionizing and non-ionizing radiation. The electromagnetic spectrum is a way to categorize all types of electromagnetic radiation based on their energy levels. Each object in the universe emits or absorbs electromagnetic radiation in a unique manner, creating a spectral signature. The non-ionizing part of the spectrum includes radio waves, which are used in communication systems like television and radio, microwaves, which serve in microwave ovens and wireless communication, and infrared light, which plays a role in night vision technologies. Visible light, which is the part of the spectrum visible to the human eye, and ultraviolet, UV light, which can cause chemical changes but doesn't fully ionize atoms, are also included in this spectrum. At the higher end of the electromagnetic spectrum, X-rays and gamma rays are the most energetic forms of radiation. These high-energy radiations are fully ionizing, capable of breaking chemical bonds and causing severe damage to biological tissues. However, even ultraviolet light, classified as non-ionizing, can still damage biological molecules and increase the risk of conditions like cancer. This is the reason why prolonged exposure to ultraviolet radiation from the sun can lead to skin damage, DNA mutations, and, in the worst cases, skin cancer. Infrared light, or IR, falls between visible light and microwaves on the electromagnetic spectrum. Its wavelengths range from just over 0.7 of a micrometer to 300 micrometers, meaning infrared light has a lower frequency than visible light, but a higher frequency than microwaves. One of the most intriguing aspects of infrared radiation is that it can be sensed as heat. Certain animals, like pit vipers, have specialized heat-detecting organs known as pits, which allow them to sense the body heat of their prey, even in the complete darkness of night. Infrared radiation is also abundant in sunlight, comprising more than half of the total energy that reaches Earth's surface at sea level. Of the total solar energy received, about 53% is infrared radiation, with 44% being visible light and only 3% ultraviolet radiation. Microwaves, another type of electromagnetic radiation, have wavelengths ranging from 1 millimeter to 1 meter. They occupy a broad frequency range between 300 MHz MHz and 300 GHz GHz, which includes ultra-high frequency UHF and extremely high frequency EHF waves, sometimes referred to as millimeter waves. And These waves are indispensable in modern technology, powering systems like satellite communication, radar, and even the microwave ovens that heat our food. Finally, radio waves, the longest of all electromagnetic wavelengths, are produced by phenomena such as lightning strikes or energetic processes occurring in outer space. Like all forms of electromagnetic radiation, radio waves travel at the speed of light and can have significant effects on communication, navigation, and much more in our interconnected world. In the vast and intricate web of radiation, whether ionizing or non-ionizing, the constant interplay between particles and matter shapes the very essence of the universe, that constantly revealing new mysteries and dangers that we continue to study and understand. However, humans have learned to manipulate and generate radio waves, which serve a variety of essential purposes in our modern world. Radio waves are the backbone of numerous communication technologies that we rely on daily. These include AM and FM radio, television broadcasts, radar systems, and wireless internet. Essentially, any wire that carries an alternating current can unintentionally emit radio waves, which is why electronic devices like microwaves or computers can sometimes cause interference with radio signals. Different types of radio waves behave uniquely when they travel through Earth's atmosphere. Long radio waves, for instance, have the ability to bend around the curvature of the Earth, providing reliable coverage over vast areas. In contrast, shorter radio waves reflect off the Earth's surface and the ionosphere, which allows them to travel over great distances. However, waves with extremely short wavelengths do not bend or reflect as easily, meaning they require a direct line of sight to transmit effectively. Radio waves are classified by their frequencies, and one of the lowest frequency categories is known as very low frequency, VLF waves. These waves range from 30 Hz to 3,000 Hz, with corresponding wavelengths that span from an enormous 100,000 meters, or 100 kilometers, down to 10,000 meters, or 10 kilometers. Because of the limited bandwidth in this frequency range, VLF waves are primarily used for simpler, low-bandwidth applications such as radio navigation. On the other end of the spectrum, extremely low-frequency ELF waves operate at frequencies from 3 Hz to 30 Hz, with wavelengths extending from 10 million meters, 10,000 kilometers, down to just 1 million meters, 1,000 kilometers. These ultra-low frequency waves are remarkable in that they can penetrate deeply into the Earth and even travel underwater. This makes them particularly useful for communication with submarines, especially in situations where traditional communication methods are ineffective. In fact, the military has constructed massive ELF antennas, like the one in Michigan, to send slow but vital messages to submarines that might otherwise be unreachable. While radio waves are essential for communication, another type of electromagnetic radiation that plays a crucial role in our daily lives is thermal radiation, which is often referred to as infrared radiation. This form of radiation is naturally emitted by all objects based on their temperature. Any object that generates heat, whether it's a stove, a heater, or even the human body, emits infrared radiation. This is why we can feel the warmth of a heater or a hot metal object without directly touching it. The glowing red heat emitted by an electric heater or a metal object heated in a fire is a prime example of infrared radiation. The underlying mechanism behind thermal radiation is the movement of charged particles inside atoms, which generates electromagnetic waves. Even relatively low-energy thermal radiation can have profound effects. For instance, when it heats certain materials to high enough temperatures, it can cause ionization, the process of stripping electrons from atoms. This ionization phenomenon is visible in flames, where the heat causes gases to glow and form plasma. Thermal radiation also plays a key role in the process of browning food, which involves complex chemical reactions, including ionization at elevated temperatures. Black body radiation is another fascinating aspect of electromagnetic radiation. It refers to the radiation emitted by an idealized object known as a black body, which absorbs and emits the maximum possible amount of radiation at all wavelengths. The intensity and color of the radiation emitted by such an object depend entirely on its temperature. At room temperature, a black body would appear completely black because it absorbs all visible light and doesn't emit enough radiation to be detectable by the human eye. However, as the temperature of the object increases, it begins to glow. This glowing is what we observe in stars. The color of a star is directly tied to its temperature. A relatively cool star at around 2500 degrees Kelvin would emit a red glow, while our sun, with a surface temperature of about 5800 degrees Kelvin, shines with a yellow hue. Hotter stars with temperatures around 15,000 degrees Kelvin appear blue-white. The concept of light existing beyond the visible spectrum was first discovered in the early 19th century. The pioneering astronomer William Herschel made a groundbreaking discovery in 1800 when he used a prism to separate sunlight into its component colors. He placed a thermometer just beyond the red part of the spectrum and found that the temperature was higher there. This experiment led to the realization that there was an invisible form of radiation beyond red light, infrared radiation. A year later, in 1801, German scientist Johann Wilhelm Ritter made a similar discovery, but on the other end of the spectrum. Ritter noticed that invisible rays beyond violet light could darken silver chloride, a chemical compound, much more quickly than violet light could. This marked the first evidence of ultraviolet radiation, which would later become pivotal in fields like photography and chemistry. Radio waves themselves were first artificially generated in 1887 by German scientist Heinrich Hertz. Hertz built electrical circuits designed to produce oscillating currents that followed the mathematical predictions laid out by James Clerk Maxwell in his famous equations. A few years later, in 1895, Wilhelm Röntgen made another monumental discovery when he uncovered X-rays. While experimenting with high-voltage electrical currents in an evacuated glass tube, Röntgen noticed that a nearby fluorescent plate began to glow. This was the first clue that certain mysterious rays could pass through soft tissues, but not bones, leading to the development of X-ray imaging, a tool that has since become indispensable in medicine. In 1896, Henri Becquerel discovered that certain minerals emitted invisible rays that could penetrate black paper and expose photographic plates. His student, Marie Curie, later identified that this effect was caused by certain elements naturally emitting energy, a phenomenon which she termed radioactivity. Over time, scientists delved deeper into the nature of these mysterious rays. In 1900, Henri Becquerel proved that beta rays were actually high-speed electrons. Then, in 1909, Rutherford and Thomas Royds showed that alpha rays were essentially helium atoms missing their electrons. A few years later, in 1914, Rutherford and Edward Andre discovered that gamma rays were a type of radiation similar to X-rays, but with even shorter wavelengths and higher energy. As the 20th century progressed, scientists also came to understand that radiation originating from outer space, what we now call cosmic rays, was constantly bombarding our planet. In 1912, Victor Verhesse proved their existence by taking an electrometer high into the atmosphere aboard a balloon. The discovery of cosmic rays changed the way scientists viewed the universe, opening up new avenues of exploration. Over the years, more breakthroughs followed. In 1932, James Chadwick discovered the neutron, a particle with no electric charge, and shortly thereafter, scientists studying cosmic rays using cloud chambers discovered even more particles, including positrons, muons, and pions. As technology advanced, particularly in the second half of the 20th century, new types of radiation were created in particle accelerators. These accelerators allowed scientists to explore and generate radiation on a much higher level than ever before, further expanding our understanding of the electromagnetic spectrum and the universe around us.